1. The moon rang like a bell when Apollo crashed into it. Why did the moon sound like a giant bell when Apollo astronauts crashed a module against its surface? In 1969, after the Apollo 12 mission, NASA conducted an experiment that would reveal something completely unexpected about the internal structure of our natural satellite. What they discovered challenged everything scientists thought they knew about how celestial bodies should behave. After Charles Conrad and Alan Bean returned from the Intrepid lunar module to the Yankee Clipper command module, NASA executed a planned maneuver. The empty ascent stage of the lunar module was deliberately launched back to the moon's surface. The objective was to create a measurable impact that the newly installed seismometers could detect. The estimated impact energy was equivalent to 1 ton of TNT. What happened next surprised all the scientists involved. The seismometers recorded vibrations that lasted more than 30 minutes intensely. Weaker signals continued for almost a full hour. For comparison, when you strike a bell on Earth, it vibrates for a few seconds and then stops. The moon reverberated for more than 55 minutes. Maurice Ewing, co-director of the seismic experiment, described the phenomenon with a phrase that became famous. He said the moon rang like a bell after the impact. This was not a casual poetic description. It was the best way to explain a completely anomalous physical behavior that no one had predicted. Why did this happen? The answer lies in the moon's internal structure. On Earth, our planet has wet, partially molten, and dense layers that absorb seismic waves quickly. Typical terrestrial earthquakes last only a few minutes. The moon, on the other hand, is extremely dry, and its crust is highly fractured by billions of years of meteorite impacts. These fractures create a porous structure that allows seismic waves to spread and reverberate through the rocky material for prolonged periods. There is no water or viscous layers to dampen the vibrations. The impact energy simply continued ricocheting through the moon's crystalline and fractured structure. The experiment was repeated with the Apollo 13 mission. When the third stage of the Saturn V rocket was launched against the lunar surface, the impact was even greater. This collision generated a force equivalent to 11 tons of TNT. The seismometers recorded reverberations that lasted more than 3 hours. The seismic waves traveled into the moon to estimated depths between 25 and 40 kilometers. Subsequent Apollo missions repeated the experiment multiple times. Apollo 14, 15, 16, and 17 also launched their lunar modules against the surface after completing their missions. Each impact provided additional data about the moon's internal composition. Scientists discovered that the moon has a crust approximately 60 kilometers thick on the far side and 40 kilometers on the near side. These experiments established something fundamental about the moon's nature. It is not simply a dead rocky sphere. It is an object with a complex, dry, and highly fractured internal structure that behaves in ways that no known celestial body replicates. The moon is, in essence, a natural cosmic bell. Behind the simple fact that the moon rang like a bell is a profound revelation about how our satellite formed and evolved. What seemed to be just a prolonged echo was actually a window into understanding billions of years of lunar geological history. The moon was not just ringing, it was telling its story through seismic waves that traveled through a dry, fractured, and ancient world. 2. The mysterious far side of the moon. Have you ever stopped to think about why we never see the other side of the moon? Throughout all human history, entire civilizations observed the same lunar hemisphere night after night. The far side remained completely invisible until 1959, when a Soviet spacecraft finally captured the first images. What these photos revealed left scientists perplexed. The moon's far side looks nothing like the side we see from Earth. While the near side is covered by dark seas of solidified lava called Maria, the far side is almost entirely covered by densely cratered bright highlands. Only 2% of the far side contains these dark basaltic plains. On the near side, this proportion reaches 31%. This dramatic contrast is known as the lunar asymmetry problem. For decades, scientists could not explain why two sides of the same celestial body looked so different. It was not just an aesthetic question, it represented a fundamental mystery about how the moon formed and evolved. The moon's synchronized rotation with Earth explains why we always see the same side. This phenomenon is called tidal locking. Earth's gravity acted on bulges in the moon over billions of years, eventually locking its rotation. The moon still rotates, but it takes exactly the same time to spin on its axis as it does to orbit Earth. This period is 27.3 days. But why are the two sides so different? The answer may lie in the thickness of the lunar crust. The far side has a crust that varies from 50 to 60 kilometers thick. The near side has only 30 to 40 kilometers in some regions. This critical difference affected volcanic lava flow billions of years ago. When the moon was young and geologically active, hot magma from the mantle tried to reach the surface. On the near side, the thinner crust allowed this material to break through and fill large impact basins. These eruptions created the dark seas we see today. On the far side, the thicker crust blocked most of the magma, preventing it from reaching the surface. Recent studies suggest another fascinating explanation. The presence of Earth in the sky of the near side may have kept that hemisphere slightly warmer during the moon's initial formation. When the moon was solidifying from a global magma ocean 4.5 billion years ago, heat-producing elements like thorium and uranium may have preferentially concentrated on the Earth-facing side. This would have facilitated prolonged volcanism in that hemisphere. The far side also contains the oldest and deepest impact basin known in the solar system. The South Pole Aitken Basin is 2,500 kilometers in diameter and 13 kilometers deep. This catastrophic impact occurred more than 4 billion years ago and was so powerful that it may have exposed material from the lunar mantle. Recent missions have revealed even more mysteries. China's Chang'e 4 mission landed on the far side in 2019 and discovered minerals that had never been seen on the lunar surface before. Analyses suggested these materials may have come from the moon's upper mantle, thrown to the surface by the impact that created the von Karman crater. Behind the simple observation that we never see the other side of the moon is a complex story of planetary formation, ancient volcanism, and cataclysmic impacts. The far side is not just different, it is a preserved time capsule that holds secrets about the early days of the solar system, when planets and moons were still forming. 3. Lunar quakes that continue for hours. Is the moon geologically dead? For decades, scientists believed our natural satellite was an inert and silent world. Then Apollo astronauts installed seismometers on the surface between 1969 and 1977. What these instruments recorded in the following 8 years completely changed our understanding of the moon's internal activity. Lunar quakes are real and happen regularly. The Apollo seismometers detected thousands of them. But they are not like earthquakes. While tremors on Earth normally last a few seconds or minutes, lunar quakes can continue for more than 10 minutes. Some weak seismic signals were detected for more than an hour. There are 4 distinct types of lunar quakes. Each type reveals something different about the moon's internal structure and dynamics. The most common are deep quakes, which occur between 700 and 1,200 kilometers below the surface. These tremors happen periodically, repeating in the same lunar location approximately every 27 days. This periodicity is not coincidence. Deep quakes are directly linked to gravitational tidal forces exerted by Earth on the moon. When the moon is at perigee, its closest point to Earth during its elliptical orbit, the gravitational pull is most intense. This stress causes fracturing and movement in the moon's partially molten interior. The second type are shallow thermal quakes. These tremors occur in the upper lunar crust and are caused by the expansion and contraction of rocky material. The moon's surface experiences extreme temperature variations. During the lunar day, which lasts 14 Earth days, temperature can reach 127 degrees Celsius. At night, it plunges to 173 degrees Celsius. These 300 degrees Celsius oscillations cause lunar rocks to expand and contract repeatedly. With billions of years of exposure to these cycles, the crust develops deep fractures. When these fractures yield under thermal stress, they generate detectable seismic tremors. These thermal quakes occur mainly during lunar dawn and dusk. The third type are meteorite impacts. The moon has no atmosphere to burn up approaching space objects. Meteorites of all sizes constantly collide with the surface at speeds ranging from 20 to 70 kilometers per second. The Apollo seismometers recorded at least 1,743 meteorite impacts between 1969 and 1977. The most intriguing and potentially most dangerous type are shallow quakes. These tremors occur at less than 200 kilometers depth and can have magnitudes up to 5.5 on the Richter scale. For comparison, that is enough energy to cause significant damage in populated areas on Earth. Fortunately, these shallow quakes are extremely rare, with only 28 detected during the entire Apollo monitoring program. The prolonged duration of lunar quakes is due to the Moon's unique structure, without water, without active plate tectonics, and with an extremely dry and fractured crust. Seismic waves propagate much more efficiently. On Earth, wet and partially, molten layers absorb seismic energy quickly. On the Moon, this energy continues ricocheting through the rigid rocky material. Recent studies using modern satellite data have revealed something even more surprising. The Moon is shrinking. As its interior slowly cools over billions of years, the total volume decreases. This creates thrust faults on the surface, similar to wrinkles on a raisin. These faults are still geologically active and may be generating lunar quakes to this day. Behind the lunar quakes that last hours is a revelation about the Moon's nature. It is not a dead world. It is a geologically active body, slowly shrinking, constantly being stretched by Earth's gravity and experiencing extreme thermal stresses. 4. Ancient lava tubes, large enough for entire cities. What exists beneath the lunar surface that could house millions of people? In 2009, the Japanese Kaguya probe detected something extraordinary. An opening on the Moon's surface revealed the entrance to a vast underground structure. Later analyses confirmed it was not just an isolated cave. It was the entrance to an entire system of tunnels extending for dozens of kilometers. These are lunar lava tubes, hollow cylindrical structures created over 3 billion years ago when the Moon was still volcanically active. When molten lava flowed beneath the surface, the outer layer cooled and solidified first. The interior remained liquid and continued flowing. When the lava source was depleted, the interior drained, leaving behind a hollow tube. But lunar lava tubes are incomparably larger than anything on Earth. The largest terrestrial tubes found in Hawaii and Iceland are at most 15 meters wide. Lunar tubes can be between 400 and 500 meters wide. Some mathematical models suggest they can reach up to 1 kilometer in diameter. Why this gigantic difference? Lunar gravity is only 1/6 of Earth's. This means rocky structures on the Moon can support much wider roofs without collapsing. The same geological forces that created modest tubes on Earth generated colossal caverns on the Moon. NASA's Lunar Reconnaissance Orbiter has identified more than 200 lunar pits since 2009. These pits are surface openings that probably lead to underground lava tubes. One of the most notable is the Marius Hills Pit, discovered in the Oceanus Procellarum region. This pit is 65 meters in diameter and 80 meters deep. Ground-penetrating radar used by NASA's Grail mission provided even more convincing evidence. Gravitational measurements detected substantial voids beneath the surface in several regions. The lava tube under Marius Hills may be 50 kilometers long and wide enough to house several cities the size of Philadelphia. These tubes offer extraordinary advantages for future human explorers. The lunar surface is constantly bombarded by cosmic radiation, solar radiation, and micro-meteorites. A surface structure would need massive shielding. Lava tubes provide natural protection. The rock above absorbs virtually all harmful radiation. Temperatures inside these tubes remain stable. While the surface oscillates between 173 and 127 degrees Celsius, the tube interiors maintain constant temperatures around 20 degrees Celsius. This is still cold by human standards, but infinitely more manageable than external extremes. Proposed missions are being developed specifically to explore these structures. NASA and the European Space Agency are studying specialized rovers that could descend into these pits using cables or controlled propulsion. Some designs include drones that would map the interior using LiDAR and high-resolution cameras. Structural stability analyses indicate that many of these tubes have remained intact for billions of years. The walls are composed of solid basalt, the same rocky material that forms the lunar mare plains. This basalt is dense, durable, and erosion-resistant. Without atmosphere, wind, or water to degrade it, the material remains virtually unchanged since its formation. Some lava tube regions may even contain water. Impact craters near the poles contain water ice in permanent shadow. It is possible that some tubes connect to regions where subsurface ice persists, If confirmed, this would transform these locations into priority targets for human settlement. The most recent discovery came from China's Chang'e 4 mission. Data from the Yutu-2 rover identified unusual materials in a small crater that may indicate partial collapse of underground structures. Spectral analyses revealed minerals consistent with exposed lava tube interiors. These gigantic tunnels are not just geological curiosities. They are potentially the key to establishing permanent human presence on the moon. But there is another even more valuable resource hidden on the moon, and it is preserved in places where sunlight has never reached for billions of years. 5. The invisible sodium tail of the moon. Crossing through space. Did you know the moon has a tail? Not a visible tail like comets, but something equally fascinating. In 1998, the Boston University Center for Space Physics made a surprising discovery. The moon is constantly releasing sodium atoms that extend hundreds of thousands of kilometers through space. This tail extends in the direction opposite the sun, exactly like a comet's tail. The lunar sodium tail is not something you can see with the naked eye. It glows at a specific wavelength of 589 nanometers, corresponding to the sodium D line. This requires specialized telescopes equipped with specific filters. When observers point these instruments at the region behind the moon, they detect a bright band of sodium emission. How can the moon, which has no significant atmosphere, have a tail? The answer lies in the interaction between the lunar surface and solar wind. Solar wind is a constant stream of charged particles ejected by the sun. These particles travel through the solar system at speeds of 400 to 800 kilometers per second. When these high-energy particles collide with the lunar surface, they transfer enough momentum to eject individual atoms from the regolith. This process is called sputtering. Sodium atoms, which are present in small amounts in lunar minerals, are particularly susceptible to this process due to their relatively low mass. The amount of sodium ejected varies dramatically. During periods of normal solar activity, the ejection rate is moderate. But when solar flares or coronal mass ejections strike the moon, the rate increases by up to 10 times. Observations made during intense solar storms showed the tail can glow significantly brighter. The sodium tail extends for at least 500,000 kilometers. To put this in perspective, the average distance between Earth and the moon is approximately 384,000 kilometers. The moon's tail extends far beyond Earth's orbit. At some moments when the geometry is correct, Earth can literally pass through the moon's sodium tail. Observations over the years have revealed that the tail has variable structure. It is not uniform. It contains bands, concentrations, and variations that correspond to specific events on the sun. When a powerful coronal mass ejection hits the moon, the tail responds within hours, becoming brighter and longer. The estimated rate of sodium loss is approximately 10 to 100 grams per second. This may not seem like much, but over billions of years it represents a significant amount of material. However, sodium is distributed in such low concentrations in the lunar regolith that this loss is negligible on geological timescales. It is not just sodium being ejected. Potassium atoms are also released and form their own tail, though weaker. Other elements like calcium, magnesium, and even silicon are sputtered from the surface. But sodium is the most easily detectable due to its distinct spectral characteristics. This discovery has important implications for understanding the lunar exosphere. The moon has an extremely tenuous atmosphere called an exosphere. It is so thin that it is essentially vacuum. The density is only 100 atoms per cubic centimeter. For comparison, Earth's atmosphere at sea level has about 10^-19 molecules per cubic centimeter. The lunar exosphere is constantly replenished by the sputtering process, but also constantly lost to space. Ejected atoms that do not have sufficient velocity to escape lunar gravity fall back to the surface. Those with enough energy escape completely and join the tail or wander through interplanetary space. More recent studies using NASA's Lunar Atmosphere and Dust Environment Explorer, LAD, confirmed that the lunar exosphere varies drastically throughout the lunar month. During lunar night, when solar wind strikes the surface directly, ejection increases. During full moon, when the moon passes through Earth's magnetosphere, ejection decreases significantly because Earth partially blocks solar wind. This invisible tail connects the moon directly to the dynamic space environment of the solar system. But solar wind and micro-meteorite impacts cause another effect on the lunar surface. They create something that proved to be one of the greatest challenges for human exploration. 6. The lunar dust that destroyed NASA equipment. What could be more harmless than dust? Apollo astronauts quickly discovered that lunar dust is nothing like dust on Earth. It is so abrasive, clingy, and penetrating that it destroyed seals, damaged spacesuits, and represented one of the greatest unexpected challenges of every lunar mission. Eugene Cernan, commander of Apollo 17, called lunar dust one of the most significant problems of lunar exploration. Lunar dust, officially called lunar regolith, consists of extremely fine particles. Average size varies between 40 and 800 micrometers. For comparison, a human hair is about 70 micrometers in diameter. These particles are products of billions of years of meteorite impacts that pulverized surface rocks into progressively smaller fragments. The problem is not just the size, it is the shape of the particles. On Earth, dust and sand are smoothed by water and wind over time. Terrestrial particles are rounded and relatively smooth. Lunar dust has never been exposed to water or wind. Each particle maintains the sharp and irregular edges created by the impact that formed it. Under an electron microscope, lunar regolith particles look like fragments of broken glass. They are angular, jagged, and coated with even smaller fragments. These sharp edges act like microsaws. When dust is pressed against any material, it cuts, scratches, and wears. Harrison Schmitt, geologist and Apollo 17 astronaut, experienced another serious problem. After returning to the lunar module covered in dust, he inhaled some particles. He immediately developed what he described as lunar hay fever. His eyes became irritated, his throat itched, and he sneezed repeatedly. The symptoms disappeared after a few hours, but revealed that lunar dust is irritating to human tissues. The dust also has an unusual electrical property. Ultraviolet radiation from the sun and solar wind electrify the particles. This creates an electrostatic charge that makes dust stick to practically everything. Astronauts reported it was impossible to remove dust from spacesuits. It adhered to helmet visors, instruments, and interior surfaces of the lunar module. Spacesuit joints and seals were particularly affected. Dust penetrated the rotating joints of shoulders, elbows, and knees. The abrasive grains began wearing down rubber and nylon seals. After just a few lunar walks, suits showed significant signs of degradation. Engineers estimated the suits would not withstand much more than the missions lasted. The problems did not stop at suits. Scientific instruments exposed to dust experienced overheating. Dust on surfaces of solar panels and thermal radiators significantly degraded their efficiency. Cameras became covered, reducing image quality. Even lunar rock samples were contaminated by electrically charged surface dust. The situation inside lunar modules was worse than imagined. When astronauts depressurized after walks, dust covering their suits floated in. Microgravity, it spread throughout the cabin. Astronauts reported the dust smell was distinctive. Some compared it to the smell of burnt gunpowder or wet ashes. Later analyses on Earth revealed why the dust was so harmful. Lunar regolith contains glass fragments created by high-velocity impacts. When meteorites strike the surface at dozens of kilometers per second, extreme heat instantly melts rock. The molten material splashes and quickly solidifies in vacuum, forming small spheres and volcanic glass fragments. These glass fragments are extremely hard. On the Mohs hardness scale, volcanic glass scores between 5 and 6. This is hard enough to scratch most plastics, rubbers, and even some soft metals. When pressed against rubber seals or nylon fabrics, the glass literally cuts the material at microscopic level. Recent studies showed lunar dust can also be toxic in prolonged exposures. Experiments with human lung cell cultures exposed to simulated lunar regolith revealed inflammatory effects. Sharp particles can physically damage cells, and certain minerals present in regolith can trigger immune responses. For future long-duration lunar missions, dust represents a critical engineering challenge. NASA is developing electrostatic coatings that repel charged particles. Other concepts include laser cleaning systems that would vaporize dust from surfaces. Some spacesuit designs incorporate external porches, where astronauts would remove outer layers before entering habitats. Dust is not just a surface nuisance. It infiltrates everything, damages equipment, and represents potential health risks. But beneath this problematic layer of regolith, the moon hides something even more puzzling. magnetic fields that should not exist in a world that lost its global magnetism billions of years ago. 7. Unexplained buried magnetic anomalies. Why do powerful magnetic fields exist in random places on the lunar surface? The moon has no global magnetic field. Its core cooled billions of years ago and stopped generating the magnetic dynamo that would protect the satellite. However, spacecraft orbiting the moon have detected more than 300 localized magnetic anomalies scattered across the surface. Some are as strong as Earth's magnetic field in certain regions. These magnetic anomalies are not uniformly distributed. They concentrate primarily in the highlands of the far side and in specific regions near large impact basins. The most intriguing pattern is that many anomalies appear exactly on the opposite side of the largest impact basins. The Mare Imbrium Basin, for example, has a significant concentration of magnetic anomalies directly on the opposite side of the moon. This geographical correlation led scientists to propose the antipodal impact theory. When a giant asteroid collides with the moon, it generates shock waves that propagate through the entire body. These waves travel through the surface and interior, eventually converging at the point exactly opposite the impact. The concentrated energy at this antipodal point may have been sufficient to melt and vaporize rocks. When iron-rich rocks are heated beyond their Curie temperature and then cool in the presence of a magnetic field, they retain permanent magnetization. If the moon still had a global magnetic field when these giant impacts occurred 3.8 to 4.1 billion years ago, the remagnetized rocks could have captured and preserved that field. But this theory does not explain all anomalies. Some have no correlation with known impact basins. Others are too strong to be explained only by impact magnetization. The Reiner gamma anomaly is particularly puzzling. It is one of the moon's most intense magnetic features, but there is no associated crater or evidence of recent impact in that region. Reiner gamma is also associated with a distinctive visual phenomenon called a lunar swirl. The surface in this region appears significantly brighter than the surrounding regolith. These swirls form sinuous patterns extending for dozens of kilometers. The localized magnetic field may protect the surface from solar wind, preventing the gradual darkening that affects the rest of the exposed regolith. Recent measurements from the Lunar Prospector mission revealed that some magnetic anomalies have intensities up to 300 nanoteslas. For comparison, Earth's magnetic field at the equator is approximately 30,000 nanoteslas. Although this is only 1% of Earth's strength, it is surprisingly strong for a celestial body without an active dynamo. The three-dimensional structure of these anomalies remains poorly understood. Orbital data provide only measurements of field intensity at spacecraft altitude. The depth of buried magnetic sources, their exact geometry, and mineral composition remain speculative. Some models suggest the sources are buried at depths of 10 to 30 kilometers below the surface. Proposed experiments include landing magnetometers directly on anomalies to measure the field in high resolution. Missions that drill a few meters into the regolith could recover magnetized samples and determine their mineralogical composition. Laboratory analyses would reveal the intensity and direction of the ancient magnetic field captured in the rocks. An alternative theory suggests comets could be responsible. When a volatile-rich comet collides with the lunar surface, the impact would instantly vaporize large amounts of ice. The generated plasma could create intense temporary magnetic fields. If rocks in the impact zone were heated and then quickly cooled, they could capture these transient fields. Another hypothesis involves short-lived localized dynamos. If pockets of iron-rich molten magma persisted in the lunar upper mantle after core solidification, convective movements in these pockets could generate regional magnetic fields. These localized dynamos would function for only a few million years before cooling completely. Measurements of lunar samples returned by Apollo missions confirm that some lunar rocks are strongly magnetized. Paleomagnetic analyses of basalts collected at different locations revealed that the moon had a global magnetic field between 3.6 and 4.2 billion years ago. The intensity of this ancient field may have been comparable to modern Earth's. These magnetic anomalies are not just scientific curiosities. They provide crucial clues about the moon's thermal and evolutionary history. If the moon had an active dynamo for hundreds of millions of years, its interior must have been significantly hotter than simple models predict. But what could have generated so much internal heat remains a fundamental question. While scientists debate the sources of these magnetic anomalies, there is something even more surprising hidden in the moon's darkest places. Billions of tons of a resource essential for life. 8 billions of tons of water ice in permanent shadow. Is there water on the moon? For decades, scientists believed the moon was completely dry. Then, in 2009, NASA's El-Quros mission deliberately crashed a rocket into a crater on the lunar south pole. The debris plume that rose contained something unexpected. Water, not just molecular traces, but significant concentrations of water ice preserved for billions of years. These discoveries concentrate in permanently shadowed regions. At the bottom of deep craters near the lunar poles, sunlight never reaches. The moon's axial tilt is only 1.54 degrees, significantly less than Earth's 23.5 degrees. This geometry creates locations where the sun never appears above the horizon. Temperatures in these permanently shadowed regions drop to extreme values. Measurements from the Lunar Reconnaissance Orbiter mission recorded temperatures as low as 248 degrees Celsius in Hermit Crater near the North Pole. This is one of the coldest places in the solar system, colder even than Pluto's surface at certain times. In these frigid conditions, water molecules can remain stable for billions of years. Any volatile that enters these cold traps becomes permanently frozen. Comets colliding with the moon deposit water. Asteroids rich in hydrated minerals contribute hydroxyl molecules. Solar wind itself implants hydrogen atoms into the regolith, which can combine with oxygen to form water. But how much ice really exists? Estimates based on neutron measurements by the Lunar Prospector mission suggest there may be between 100 million and 600 million metric tons of water ice at the lunar poles. To put this in perspective, 100 million tons of water would be enough to supply 100,000 people for 100 years. Ice concentration varies dramatically from location to location. Some regions may have up to 30% ice mixed with regolith. Others have only a few percent. The deposits are not pure ice layers on the surface. The ice is mixed with lunar soil, buried in the first centimeters to meters of regolith. Cabeus Crater, where the El-Quros mission impacted, revealed a complex composition. Besides water, instruments detected carbon monoxide, carbon dioxide, ammonia, methane, and even traces of mercury and silver. This mixture suggests volatile materials were deposited over billions of years by multiple sources. More recent discoveries have further complicated the picture. In 2020, NASA's Stratospheric Observatory for Infrared Astronomy, ESOFIA, detected molecular water on the moon's sunlit surface. The concentration is low, between 100 and 400 parts per million, but its presence was completely unexpected. How can water exist on surfaces exposed to sunlight? Temperatures during the lunar day reach 127 degrees Celsius, well above water's boiling point in vacuum. The proposed explanation involves microscopic glass beads in the regolith. Water molecules can become trapped inside these beads, protected from direct solar radiation. Another possibility involves micro-cold traps. Even in illuminated regions, small shadows created by rocks, boulders, or surface roughness can maintain temperatures low enough to retain ice. These micro-traps may be only centimeters in diameter, but collectively could contain significant amounts of water. The origin of this water remains debated. Comets striking the moon contribute ice directly. Each comet impact deposits thousands of tons of water, though most evaporates on impact. Carbonaceous asteroids contain hydrated minerals that release water when heated by impacts or solar radiation. Solar wind also plays an important role. Hydrogen protons in solar wind collide with oxygen atoms in the lunar regolith, forming hydroxyl and water through chemical reactions. This process happens constantly across the entire sunlit surface. The water produced can migrate through the tenuous lunar exosphere until eventually becoming trapped in cold regions. Isotopic measurements of El-Quros samples provided clues about water sources. The ratio of deuterium to hydrogen in lunar water is consistent with both cometary sources and solar wind. This suggests multiple processes have contributed over geological time. For future crewed missions, this ice represents a critical resource. Water can be drunk, but can also be split into hydrogen and oxygen through electrolysis. Oxygen serves for breathing and rocket fuel. Hydrogen can be fuel or combined with carbon dioxide to produce methane. A lunar base near ice deposits would be significantly more sustainable. Prospecting missions are being planned to map ice deposits in high resolution. Specialized rovers equipped with neutron spectrometers and ground-penetrating radar will identify the richest concentrations. Drills will extract samples from up to 2 meters deep to determine the vertical distribution of ice. This frozen water hidden in the moon's darkest craters may make prolonged human presence possible. But the presence of water today raises another intriguing question. Did the moon ever have an atmosphere thick enough to maintain liquid water on the surface? 9. The moon's disappeared atmosphere. Did the moon ever have an atmosphere? The idea seems absurd at first glance. Today, the moon is practically a perfect vacuum. Surface atmospheric pressure is only 3x 10^15 atmospheres. For comparison, the best vacuum created in terrestrial laboratories is approximately 10 or 11 atmospheres. The moon has a naturally better vacuum than anything we can produce artificially. But growing evidence suggests that billions of years ago, the situation was dramatically different. When the moon was young and geologically active, massive volcanic eruptions poured gases onto the surface. Between 3.5 and 4 billion years ago, these volcanic events may have created a significant temporary atmosphere. Analyses of lunar samples revealed something surprising about the scale of ancient lunar volcanism. The dark seas we see on the moon, called Maria, are vast plains of solidified basalt. These plains are up to 1 kilometer thick in some locations. The total volume of lava that flooded these basins is estimated at approximately 10 million cubic kilometers. When basaltic lava erupts, it releases not just molten rock. Dissolved gases escape from the magma in a process called degassing. On Earth, volcanic eruptions release primarily water vapor, carbon dioxide, and sulfur dioxide. Analyses of volcanic glasses and Apollo lunar samples revealed that lunar magma contains significant amounts of volatile compounds. Studies published in 2017 calculated degassing rates during peak lunar volcanism. During periods of intense volcanic activity, the moon could have released up to 10 million tons of gases per year. The main components would be carbon monoxide and water vapor, with smaller amounts of hydrogen, sulfur, and other volatiles. If these gases were released faster than they could escape to space, they would accumulate temporarily. The moon's low gravity, only 1/6 of Earth's, means gases can escape more easily. Molecules moving faster than the lunar escape velocity of 2.38 kilometers per second simply fly into space. But during the most intense volcanism periods, the gas release rate may have exceeded the escape rate. Atmospheric models suggest the moon could have developed an atmosphere with pressure up to 10 millibars. This is approximately 1% of Earth's atmospheric pressure at sea level, comparable to pressure in the terrestrial stratosphere at 30 kilometers altitude. This temporary atmosphere would have lasted between 70 and 100 million years. During this period, atmospheric pressure may have been sufficient to maintain liquid water on the surface in some regions. Temporary lakes could have existed in the lowest areas of the lunar seas. Water would eventually evaporate, but for a few million years, parts of the moon could have been genuinely wet. The composition of this ancient atmosphere would be hostile to life as we know it. Rich in carbon monoxide and poor in oxygen, it would not be breathable. Temperatures during the lunar day would still reach extreme values, but the mere presence of an atmosphere and liquid water, even temporarily, represents a fascinating chapter in lunar history. What happened to this atmosphere? The moon's weak gravity could not retain it indefinitely. Without a global magnetic field to protect it from solar wind, charged particles from the sun collided directly with atmospheric molecules. These collisions transferred enough energy to eject atoms and molecules into space. Additionally, solar ultraviolet radiation broke complex molecules into lighter components. Water vapor was split into hydrogen and oxygen. Hydrogen, being the lightest element, escaped easily. Oxygen reacted with minerals on the surface or also escaped gradually. When lunar volcanism decreased and eventually ceased about 1 to 2 billion years ago, the gas replenishment source was interrupted. The atmosphere continued escaping until practically nothing remained. The atmospheric loss process took tens of millions of years, but eventually the moon returned to the vacuum state it maintains today. Traces of this ancient atmosphere may still exist. Some heavy gases may have migrated to cold polar regions and frozen. Volatile deposits discovered in permanently shadowed craters may contain not just water from comets, but also ancient volcanic gases preserved as frozen time capsules. Proposed experiments involve analyzing isotopes in polar deposits to determine their origins. Gases from volcanic sources would have distinct isotopic signatures from gases brought by comets. If volcanic gases are identified, they would confirm that the ancient atmosphere really existed and left detectable deposits. The idea of a moon with atmosphere and possibly temporary lakes challenges our image of an eternally arid and dead satellite. For tens of millions of years, the moon may have been a genuinely different world, with active geological processes and a dynamic surface environment. But this atmosphere depended on a process that also requires another feature the moon lost long ago: its global magnetic field. 10. Why the moon lost its global magnetic field. How does a celestial body lose its magnetic shield? Earth possesses a robust magnetic field generated by convective movements in the outer core of liquid iron. This field protects us from solar wind and cosmic radiation. The moon, on the other hand, has virtually no global magnetic field, but evidence from lunar rocks proves this was not always true. Lunar samples returned by Apollo missions contain a magnetic surprise. When igneous rocks cool from a molten state in the presence of a magnetic field, ferromagnetic minerals within them align with that field. This magnetization becomes permanently recorded, creating a fossil record of the ancient magnetic field. Paleomagnetic analyses of lunar basalts revealed that between 4.2 and 3.5 billion years ago, the moon had a magnetic field with intensity comparable to Earth's. Some samples indicate field intensities up to 70 microteslas. Earth's current magnetic field is approximately 50 microteslas. This means the ancient lunar magnetic field was surprisingly strong. How did the moon generate such a powerful field? The answer lies in the lunar core. Seismic data from Apollo missions and modern gravitational measurements confirm the moon has a metallic core. This core consists of a solid inner region with radius of approximately 240 kilometers and a liquid outer layer about 90 kilometers thick. For a core to generate a magnetic field through a dynamo, it needs three essential ingredients. First, an electrically conductive material like liquid iron. Second, movement of this material, typically through thermal or compositional convection. Third, rotation of the celestial body, which organizes convective movement into patterns that generate magnetic field. The moon possesses all these ingredients, but there is a fundamental problem. The lunar core is very small. Earth's core represents 55% of the planetary radius. The lunar core represents only 20% of the moon's radius. A small core cools more quickly and has less material to generate sustained convection. So how did the moon maintain an active dynamo for hundreds of millions of years? A popular theory involves the process called core precession. In the first billions of years after its formation, the moon was significantly closer to Earth. The distance was only 25,000 to 30,000 kilometers compared to the current 384,000 kilometers. At this proximity, Earth's tidal forces on the moon were immensely stronger. These forces could have caused oscillations at the boundary between the lunar mantle and liquid core. This oscillatory movement, combined with lunar rotation, could have stirred the core enough to generate convective movements capable of producing a magnetic dynamo. Another possibility involves crystallization of the inner core. As the lunar core cooled, solid iron began to crystallize at the center. This process releases latent heat and expels lighter elements into the liquid outer core. These compositional differences create compositional convection, which can be more efficient at generating magnetic fields than purely thermal convection. But the lunar dynamo did not last. Analyses of younger samples show the magnetic field weakened dramatically about 3.1 billion years ago. By around 2.5 billion years ago, the field had practically disappeared. What caused this magnetic death? The most likely explanation is simple. The lunar core cooled too much. Small bodies lose heat more rapidly than large bodies due to their greater surface area to volume ratio. As the core cooled, convective movements weakened. Eventually, convection stopped completely and the dynamo shut off. The loss of the magnetic field had profound consequences. Without magnetic protection, solar wind began interacting directly with the lunar surface. High-energy particles from the sun struck the regolith, altering its chemical composition. Atoms were sputtered from the surface. Any remaining atmosphere was gradually stripped away by solar wind. The lunar regolith became progressively matured by direct exposure to solar wind. This process creates nanophase impact glass and metallic iron nanoparticles that darken the soil. Rocks exposed on the lunar surface without magnetic protection show distinctive signs of this space weathering. Some scientists propose the lunar magnetic field may have had brief resurgences after its main decline. Giant asteroid impacts could have temporarily reheated parts of the mantle or core, restarting localized convection for a few million years. Paleomagnetic evidence from some younger rocks suggests pulses of increased magnetic intensity. The Moon's dead magnetic field also affected its ability to retain an atmosphere. On Earth, the magnetic field deflects most solar wind, drastically reducing atmospheric loss. Mars lost its global magnetic field billions of years ago and subsequently lost most of its atmosphere. The Moon followed a similar fate. But even without atmosphere or magnetic field, the Moon continues to surprise observers with mysterious lights and transient phenomena that defy simple explanations. 11. Transient lunar phenomena observed for centuries. What causes mysterious lights on the Moon? For more than 400 years, astronomers have reported strange observations of transient events on the lunar surface. Flashes of light, color changes, localized hazes, and anomalous glows appear temporarily and then disappear. These events are called transient lunar phenomena, or LTPs. The first documented scientific record dates from 1587, when astronomers reported a bright flash in the region of the Moon, then called the dark spot. Since then, thousands of observations have been cataloged. Some events last only seconds, others persist for hours. Most occur in specific locations that appear to be geologically active or unusual. One of the regions most frequently associated with LTPs is Aristarchus crater. Located on the edge of Oceanus Procellarum, Aristarchus is one of the Moon's brightest features. Observations of reddish glows, temporary obscurations, and light flashes in this crater have been reported hundreds of times since the 17th century. In 1958, Russian astronomer Nikolai Kozyrev was observing Alphonsus crater when he detected a spectrum of gaseous emission. For approximately 1 hour, he recorded spectral lines consistent with fluorescing carbon molecules. This suggested gases were being temporarily released from the lunar surface. During Apollo missions, the astronauts themselves reported unusual observations. While orbiting the Moon in 1972, astronaut Ron Evans reported a bright flash near Grimaldi crater. Simultaneous observations from Earth did not detect the event, suggesting it was extremely brief or too localized to be captured by terrestrial telescopes. Explanations for these phenomena vary widely. One of the most probable causes are meteorite impacts. The Moon is constantly bombarded by space fragments. When a meteorite strikes the surface at dozens of kilometers per second, the impact generates a bright flash of visible light. This flash lasts only a fraction of a second, but can be seen from Earth if large enough. Systematic monitoring programs have confirmed that meteorite impacts are relatively common. Since 2005, NASA operates telescopes dedicated to detecting lunar impact flashes. They have recorded more than 400 confirmed events. The largest observed impact occurred on March 17, 2013, when a small rock-sized meteorite struck the Moon, creating a flash as bright as a magnitude 4 star. But meteorite impacts do not explain all LTPs. Some events last too long to be impacts. Others show specific coloration, like reddish or orange glows, that are not consistent with impact plasma. Gradual brightness changes in specific regions suggest different processes. An alternative explanation involves lunar degassing. Although the Moon is geologically inactive today, small amounts of gas may still be released from subsurface reservoirs. When the Moon experiences maximum tidal stresses, fractures in the crust can open slightly, allowing gas to escape. These gases could reflect sunlight in unusual ways or fluoresce under ultraviolet radiation. Experiments performed by the Lunar Atmosphere and Dust Environment Explorer (LADEE) mission detected intermittent increases in lunar exosphere density. Some of these events were not clearly associated with impacts or other known processes. This suggests sporadic gas releases may actually occur. Another possibility involves electrification of lunar dust. Solar radiation and solar wind charge the regolith electrostatically. Under certain conditions, charged dust particles can be levitated above the surface. Clouds of electrically charged dust could scatter light in anomalous ways, creating temporary glows or obscurations. Observations of diffuse halos near the terminator, the line between day and night on the moon, support the levitated dust theory. When the sun is low on the lunar horizon, electric fields form at the terminator due to charge differences between illuminated and dark regions. These fields could temporarily suspend dust. Critics argue many historical LTPs were observational artifacts. Terrestrial atmospheric distortions, optical aberrations in old telescopes, or simply misinterpretations could explain many reports. Earth's atmosphere causes scintillation and apparent color changes, especially for objects near the horizon. However, modern observations with sophisticated equipment have confirmed some transient phenomena are genuine. Automated detection systems eliminate human bias. Multiple independent observations of the same event increase reliability. Spectral analyses provide objective data about the nature of detected light. Citizen science programs now invite amateur astronomers to systematically monitor the moon. When events are detected by multiple independent observers at different geographical locations, the probability they are real increases significantly. These collective efforts are building a modern database of LTPs with much more rigorous documentation. Transient lunar phenomena represent one of the few dynamic processes still active on the moon. While meteorite impacts explain many events, others remain mysterious. The moon may not have active volcanoes or plate tectonics, but it is not completely inert. Small processes continue altering its surface and atmosphere in subtle ways. These transient events remind us that even apparently dead worlds still have secrets to reveal, just like the invisible processes through which the moon continues shaping our own planet. 12. Impact basins. Older than life on Earth. How long can a scar last? On Earth, mountains are eroded, oceans change shape, and continents move. Impact craters disappear in a few million years. On the moon, scars of cosmic violence remain virtually unchanged for more than 4 billion years. The largest lunar impact basins are older than any rock found on Earth's surface and predate the emergence of life on our planet. The South Pole Aitken Basin is the oldest and largest impact structure on the moon. With 2,500 kilometers in diameter, it extends across almost a quarter of the lunar circumference. The basin's depth varies between 8 and 13 kilometers below the surrounding highlands. If this crater existed on Earth, it would cover all of Western Europe. The estimated age of the South Pole Aitken Basin is approximately 4.3 billion years. For context, Earth is 4.54 billion years old. This impact occurred only 250 million years after the solar system's formation. At the time, both Earth and the Moon were still being regularly bombarded by massive objects remaining from planetary formation. The asteroid that created this basin was probably between 150 and 200 kilometers in diameter. It collided with the Moon at an estimated velocity of 15 kilometers per second. The energy released was equivalent to billions of nuclear bombs. The impact was so powerful that fragments of the crust and possibly lunar mantle were ejected into space. Analyses from China's Chang'e 4 mission, which landed within the basin in 2019, revealed unusual minerals. The U-22 rover detected olivine and low-calcium pyroxene in proportions suggesting origin in the upper mantle. The impact that created the basin was deep enough to excavate material from dozens of kilometers below the original crust. Other ancient basins include Imbrium, Serenitatis, and Crisium. The Imbrium Basin, one of the most visible from Earth, is approximately 1,945 kilometers in diameter. It formed about 3.85 billion years ago when a 250-kilometer diameter asteroid struck the Moon. The impact was so violent it ejected material across the entire near hemisphere. Debris from the Imbrium impact was found at multiple Apollo landing sites. Samples collected hundreds of kilometers away contain fragments of melted rock with chemical compositions identical to basin material. Radiometric dating of these samples confirms they all formed in the same catastrophic event, 3.85 billion years ago. This period of intense bombardment is called the Late Heavy Bombardment. Between 4.1 and 3.8 billion years ago, the inner solar system experienced a dramatic increase in impact rates. The probable cause was an orbital reorganization of the giant planets that destabilized the asteroid belt and sent thousands of massive objects toward the inner solar system. Earth suffered the same bombardment, but evidence was erased. Plate tectonics constantly recycle Earth's crust. Erosion by water and wind wears away surface features. The oldest oceanic crust is only 200 million years old. The oldest continental rocks are 4 billion years old, but no craters from that era survived intact. The moon preserves this lost record. Without atmosphere, without liquid water, without plate tectonics, impact basins remain frozen in time. Studying these structures is not just learning about lunar history. It is understanding the violent history of the entire inner solar system, including primitive Earth. The basins also profoundly shaped lunar geological evolution. They created depressions that later filled with basaltic lava, forming the dark seas. They fractured the crust in patterns that influenced subsequent volcanism. Heat generated by impacts may have partially melted the upper mantle, creating magma reservoirs that took millions of years to solidify. Some of these basins may contain valuable resources. Impacts that penetrated deep into the crust exposed normally inaccessible materials. Rare minerals, metals, and possibly even helium-3 may be concentrated in certain regions. Future exploration missions will prioritize geologically complex areas where ancient impacts revealed the moon's deep layers. These monumental scars of cataclysmic impacts tell the story of a young and chaotic solar system. But the impacts that created these basins had another lasting effect. They altered mass distribution within the moon, creating gravitational variations that affect everything orbiting our natural satellite. These gravitational anomalies hidden beneath the surface continue to surprise scientists. 13. How the moon stabilizes Earth's tilt and seasons. Why are Earth's seasons so predictable? The answer may surprise. It is because of the moon. Without our natural satellite, Earth's axial tilt would vary chaotically over millions of years. Mars, which has 2 insignificant small moons, experiences extreme variations in its axial tilt. Earth remains stable thanks to lunar gravitational influence. Earth's axial tilt is currently 23.5 degrees. This tilt is responsible for seasons. When the northern hemisphere is tilted toward the sun, it is summer there and winter in the southern hemisphere. 6 months later, the situation reverses. This seasonal cycle has been remarkably stable for hundreds of millions of years. Computer simulations reveal what would happen without the moon. Earth's axial tilt could vary from 0 to 85 degrees over periods of millions of years. With tilt near 0, there would be no seasons. With 85-degree tilt, the poles would point almost directly at the sun at certain times of year, creating extreme climatic variations. These chaotic variations occur due to gravitational perturbations from other planets. Jupiter, Saturn, and the other giants exert tidal forces that try to modify Earth's axial orientation. In a system without the moon, these perturbations would dominate. Earth would respond to planetary influences like an unbalanced spinning top. The moon stabilizes Earth's axis through gravitational torques. Earth's equatorial bulge, caused by planetary rotation, provides a gravitational handle for the moon to exert force. This interaction keeps axial tilt relatively constant. Variations still occur, but are limited to only 1.3 degrees over 41,000-year cycles. Mars offers a dramatic example of what can happen without lunar stabilization. Martian tilt is currently 25 degrees, similar to Earth's, but studies of polar layers and sedimentary deposits indicate that over the last 5 million years, tilt varied between 15 and 35 degrees. On longer timescales, it may have reached 60 degrees or more. These extreme oscillations cause catastrophic climate changes on Mars. When tilt is low, the poles remain cold and accumulate frozen carbon dioxide. When tilt increases, poles receive more sunlight, ice sublimates, and atmospheric pressure temporarily increases. Martian climate is fundamentally unstable on geological timescales. Earth's orbital stability allowed the evolution of relatively predictable climates for billions of years. Organisms could adapt to regular seasonal patterns. Complex ecosystems developed around consistent annual cycles. Without this stability, the evolution of complex life on Earth could have been significantly more difficult or even impossible. Lunar influence is not just about axial tilt. The moon also affects precession of the equinoxes. Earth's axis executes a precession motion, like a spinning top. with a period of approximately 26,000 years. Without the moon, this period would be much shorter and more irregular, causing unpredictable changes in long-term climate patterns. But there is irony in this stabilization. The same gravitational interaction that stabilizes Earth's axis is gradually pushing the moon away. Each year, the moon recedes approximately 3.8 centimeters. Billions of years from now, when the moon is significantly more distant, its ability to stabilize Earth's axis will diminish. Fortunately, this loss of stabilization is an extremely slow process. It will take billions of years before effects become significant. On this timescale, the sun will have evolved into a red giant and engulfed the inner planets. Loss of lunar stabilization is irrelevant compared to more immediate cosmic fates. The discovery of the moon's stabilizing role has implications for the search for habitable planets. Exoplanets without large moons may experience extreme climate variations. Astronomers now consider the presence of a substantial moon as a favorable factor for habitability. Planets with proportionally large moons like ours may have more stable environments for life development. The moon does not just illuminate our nights and create tides, it functions as a giant gravitational stabilizer, keeping Earth in a relatively constant orientation for billions of years. But beyond physically stabilizing our planet, the moon also exerts more subtle and controversial influences. Its monthly cycle has been associated with strange behaviors in countless animal species. 14. The strange influence of the moon on animal behavior. Does the moon really affect animal behavior? For millennia, humans believed the full moon caused unusual behaviors. The word lunatic derives from lunar. But what modern science has discovered is that while many beliefs about lunar influences on humans are myths, hundreds of animal species synchronize their behaviors with lunar cycles in fascinating ways. The most dramatic examples come from the oceans. Corals of various species worldwide synchronize their reproduction with the full moon. On the Great Barrier Reef, mass spawning occurs on specific nights after the full moon in October or November. Billions of gametes are released simultaneously, creating an underwater snowstorm of eggs and sperm. This precise timing is not coincidence. Synchronization drastically increases fertilization chances. If each colony released gametes randomly, most would be dispersed by ocean currents before meeting. Synchronized release ensures eggs and sperm from multiple colonies mix, promoting genetic diversity. How do corals detect lunar cycles? They have no eyes or complex nervous system. Recent research identified blue light-sensitive photoreceptors called cryptochromes. These receptors detect subtle changes in lunar light intensity and spectrum throughout the month. The full moon provides a distinctive light signal that triggers internal hormonal processes. Crustaceans also demonstrate striking lunar behaviors. Horseshoe crabs emerge on East Coast U.S. beaches exclusively during high tides of full and new moons in May and June. Females deposit thousands of eggs in wet sand, males fertilize them. Subsequent waves cover the eggs, which develop protected until the next spring tide 2 weeks later. California grunion execute an even more precise reproductive ritual. They surf onto beaches during the highest tides after full and new moons. Females burrow into sand and deposit eggs. Males fertilize them. Adults return to the ocean with the next wave. Eggs remain buried for exactly 2 weeks until the next series of high tides uncovers them, at which moment they instantly hatch. But it is not just marine species. Lions in the African savanna hunt more actively during the new moon. Long-term studies documented that hunting success rates increase significantly on dark nights. The explanation is straightforward. Lions have excellent night vision, but their prey do not. Darkness provides maximum tactical advantage. Fruit bats drastically reduce their foraging activity during the full moon. Researchers in Central America documented reductions up to 70% in the number of bats leaving caves on full moon nights. Moonlight increases predation risk from owls and nocturnal hawks. Bats adjust their behaviors to minimize exposure. Migratory birds use moonlight for nocturnal orientation. Studies with GPS trackers showed many species prefer to initiate migrations during full moon. Additional light facilitates visual navigation. Birds can see geographical features like rivers, coastlines, and mountains more clearly under moonlight. Insects also respond to lunar cycles. Dung beetles use polarized moonlight to navigate. Researchers demonstrated that when the moon is visible, beetles roll their dung balls in straighter lines. When the moon is obscured by clouds, beetles follow more erratic trajectories. They literally navigate by moonlight. Some terrestrial mammals show more subtle lunar behavioral patterns. European wild boars increase their activity during new moon phases, probably to reduce exposure to predators and human hunters. Deer adjust feeding patterns, foraging more during dark nights and remaining in cover during illuminated nights. Even microscopic organisms respond to the moon. Marine polychaete larvae emerge from the ocean floor in synchrony with specific lunar phases. Zooplankton execute daily vertical migrations that are modulated by the lunar cycle. During full moon, nocturnal migration toward the surface is reduced, presumably to avoid visual predation. Mechanisms vary. Some species detect moonlight directly through photoreceptors. Others respond to tidal changes caused by lunar gravity. Some synchronize with lunar cycles through endogenous circulunar clocks, internal biological rhythms with periods of approximately 29.5 days. Lunar influence on animals is real and measurable, but for modern humans, these connections have been largely lost. Artificial light obscures natural cycles. Still, the full moon continues to influence creatures across the planet, coordinating reproductive, feeding, and migratory behaviors through light and gravitational signals. These current lunar influences on terrestrial life are echoes of a much older and more fundamental relationship: the cataclysmic event that created the moon itself. 15. The giant impact that created the moon. How was the moon born? For centuries, scientists proposed theories. Perhaps the moon formed alongside Earth. Perhaps it was captured by Earth's gravity while passing by. Perhaps it separated from Earth when our planet spun so fast that material broke off. None of these theories explained all the evidence. Then, analyses of Apollo lunar rocks revealed something surprising that pointed to a violent origin. The moon's isotopic composition is almost identical to Earth's. Isotopes of oxygen, titanium, and tungsten in lunar rocks precisely match terrestrial proportions. But the moon has much less iron than Earth. It is significantly less dense, and the moon is completely devoid of volatile elements like water, chlorine, and potassium compared to terrestrial rocks. These contradictory evidences only make sense through a specific scenario: the giant impact. Approximately 4.5 billion years ago, when Earth was only 30 to 50 million years old, a Mars-sized protoplanet collided with our planet. This object, called Theia by scientists, was approximately 6,400 kilometers in diameter, about half Earth's diameter. The collision occurred at an oblique angle at velocities of 4 to 15 kilometers per second. The impact was not head-on. If it were, both bodies would have been vaporized or melted into a single sphere. The oblique angle allowed Theia to graze Earth, tearing off the upper mantle of both bodies and ejecting enormous amounts of material into space. The energy released was beyond comprehension. The impact instantly vaporized rocks on both planets. Temperatures reached thousands of degrees Celsius. All of Earth became a global magma ocean. Theia's iron core, being denser, sank through terrestrial magma and merged with Earth's core. This explains why the moon has proportionally less iron. The ejected material, mainly from the upper mantle of both bodies, formed a debris disk around Earth. This disk contained vaporized rocks, molten magma, and solid fragments. Volatile elements evaporated in extreme heat and escaped to space. This explains why the moon is so dry and devoid of volatile compounds. Within a few hours after impact, the most distant material in the disk began to clump. Particles collided and stuck. Aggregates grew into mountain-sized blocks. These blocks collided and merged into increasingly larger bodies. The accretion process was extremely rapid in geological terms. Modern computer simulations suggest the moon formed in only 10 to 100 years after impact. Material in the disk condensed first into multiple large fragments. These fragments orbited chaotically, colliding and merging. Eventually, a dominant body emerged, gravitationally attracting all remaining material. This body was the primitive moon. The newly formed moon was incredibly close to Earth. The initial distance was only 25,000 to 30,000 kilometers compared to the current 384,000 kilometers. At this proximity, the moon would appear in Earth's sky with an angular diameter 15 times larger than today. It would cover a significant part of the sky, totally dominating the nocturnal landscape. Tidal forces were immensely stronger. Tides on primitive Earth, when oceans eventually formed, would have been hundreds of meters high. Solid Earth itself deformed visibly, rising and falling meters twice daily. The moon was also heated by tidal forces, keeping its interior molten for much longer. The giant impact theory elegantly explains the moon's characteristics. It explains why isotopic composition is similar to Earth's, both formed from the same mantle material. It explains low lunar density. The iron core was separated during the process. It explains the lack of volatiles. Extreme heat vaporized them. Additional evidence comes from Earth-Moon system dynamics. The total amount of angular momentum in the system is exactly what would be expected if a Mars-sized body collided with primitive Earth at an oblique angle. This calculation, first made in the 1970s, was one of the first clues leading to the giant impact theory. Recent analyses refined the model. Studies from 2017 suggested Theia may have formed near Earth's orbit in a region called the L4 or L5 Lagrangian point. This would explain why isotopic compositions are so similar. Theia and Earth form from the same material in the same protoplanetary disk. But some questions remain. Simulations show the moon should be composed mainly of Theia material, not Earth's. However, isotopic compositions are almost identical. This suggests Earth and Theia were extraordinarily similar, or that the impact mixed materials more thoroughly than models predict. The giant impact was possibly the most important event in Earth's history. It created the moon, which would stabilize Earth's axis and create tides that would influence life's evolution. It removed Earth's first atmosphere and completely reconfigured the planet's outer layer. It was a catastrophic reset that set the stage for everything that would come after. And after the moon formed from this cosmic cataclysm, its interior remained molten for millions of years, eventually releasing lava floods that would permanently transform its surface. 16. Ancient volcanic eruptions that created the dark seas. Why does the moon have dark spots? Anyone can see them with the naked eye. These dark regions form patterns that different cultures interpreted as faces, rabbits, or human figures. In reality, these spots are vast plains of solidified basaltic lava. They formed billions of years ago when the moon was a volcanically active world with rivers of molten rock flowing across the surface. These regions are called maria, the Latin word for seas. Early astronomers thought they were bodies of water. Galileo, observing through his telescope in 1610, named features like Mare Imbrium, Mare Serenitatis, and Oceanus Procellarum. But there is no water. The maria are fields of solidified basaltic lava covering approximately 17% of the lunar surface. Lunar volcanism began about 4 billion years ago and continued intermittently until approximately 1 billion years ago. Peak activity occurred between 3.8 and 3.1 billion years. During this period, massive eruptions flooded the largest impact basins with basaltic lava. Some of these floods deposited layers up to 1 kilometer thick. Lunar lava was different from most terrestrial lavas. It had extremely low viscosity, similar to motor oil consistency. This low viscosity allowed it to flow easily for hundreds of kilometers across the surface. Chemical analyses of Apollo samples revealed lunar lava was particularly rich in iron and titanium, which contributed to its dark coloration. The eruptions were not explosive like typical terrestrial volcanoes. The moon has no atmosphere, so there are no dissolved gases that expand violently when pressure decreases. Instead, lunar eruptions were effusive. Magma simply bubbled to the surface through fissures and spread in vast sheets of liquid lava. Some eruptions created lava fountains. When gas-rich magma erupted rapidly through narrow openings, it launched drops of molten lava dozens or even hundreds of meters into the air. In low lunar gravity, these drops traveled considerable distances before falling back to the surface. They solidified as small spheres of volcanic glass. Apollo 15 and 17 astronauts collected samples of these volcanic glass spheres. Colors vary from dark green to orange and red, depending on chemical composition. Radiometric dating of orange spheres collected by Apollo 17 indicated an age of 3.64 billion years. These small spheres are literally solidified drops of lava launched from volcanic fountains billions of years ago. Lunar volcanism was fueled by residual internal heat from the moon's formation. Additionally, radioactive decay of elements like uranium, thorium, and potassium continuously generated heat. Elevated concentrations of these heat-producing elements in the upper mantle kept regions partially molten for hundreds of millions of years. But why did eruptions fill mainly the near side? The far side has very few maria. The explanation lies in crustal thickness. The near side has thinner crust. Between 30 and 40 kilometers, the far side has 50 to 60 kilometer crust. When magma ascended from the mantle, it could penetrate the thinner crust more easily. Impact basins also played a crucial role. Giant impacts further thinned the crust in struck regions and deeply fractured underlying layers. These fractures provided pathways for magma to ascend. Additionally, heat generated by impacts may have partially melted the mantle just below basins. Mare Imbrium, one of the most prominent seas, filled the basin created by the Imbrium impact 3.85 billion years ago. But lava did not arrive immediately. Eruptions that filled Imbrium occurred between 3.8 and 3.0 billion years ago, hundreds of millions of years after impact. This demonstrates it took significant time for magma to accumulate and finally erupt. Oceanus Procellarum, the Moon's largest dark region, is not associated with an obvious impact basin. Its irregular shape suggests it may have formed through a different process. Gravitational data revealed Procellarum is located over a region where the crust is particularly thin and fractured, possibly due to ancient tectonic stresses. As volcanism decreased, eruptions became smaller and rarer. The last significant eruptions occurred approximately 1 billion years ago. Since then, the Moon has been volcanically inactive. The interior cooled too much to generate additional magma. The dark seas we see today are frozen landscapes of a volcanic past that ended when Earth was just beginning to develop complex multicellular life. These basaltic lava fields are some of the flattest terrains in the solar system. Because lava flowed freely and settled gravitationally, maria surfaces have elevation variations of only a few meters over kilometers. This makes them ideal targets for spacecraft landings and future bases. The eruptions that created the dark seas permanently transformed the Moon's appearance, and these vast lava plains now represent both a precious geological record and a potential home for future human explorations. 17. Why the far side looks completely different. What explains the dramatic difference between the two sides of the Moon? When the first images of the far side were transmitted by the Soviet Luna 3 probe in 1959, scientists were perplexed. While the near side is marked by vast, dark lava plains, the far side is almost entirely covered by densely cratered bright highlands. The difference is so pronounced it seems we are looking at two completely distinct worlds. The asymmetry is measurable and dramatic. Only 2% of the far side is covered by maria, the dark basaltic plains. On the near side, this proportion jumps to 31%. The average elevation on the far side is approximately 1.9 kilometers higher than on the near side. Crustal thickness varies from 30 to 40 kilometers on the near side, but reaches 50 to 60 kilometers on the far side. This difference in crustal thickness is the key to understanding the asymmetry. When the Moon was young and volcanically active, magma from the upper mantle tried to reach the surface. On the near side, the thinner crust offered less resistance. Magma dikes could penetrate the upper layers and erupt, filling impact basins with basaltic lava. On the far side, the thick crust acted as a barrier. The pressure necessary for magma to break through and traverse 60 kilometers of solid rock was much greater. In most cases, the magma simply did not have enough force. It stagnated at depth, cooled slowly, and solidified without ever reaching the surface. But what caused this difference in crustal thickness? The answer may lie in the Moon's initial formation. After the giant impact that created the Moon 4.5 billion years ago, the entire satellite was covered by a global magma ocean. This ocean was hundreds of kilometers deep and took millions of years to solidify. As the magma ocean cooled, lighter minerals floated to the surface, forming the crust. Denser minerals sank. The gravitational presence of nearby Earth may have influenced this process. The Earth-facing side, being pulled more strongly by terrestrial gravity, may have experienced different convection in the magma ocean. Another theory suggests Earth kept the near side slightly warmer. When the moon was very close to Earth immediately after its formation, thermal radiation from primitive Earth heated by impacts could have affected the solidification rate. The near side, constantly facing the incandescent Earth, cooled more slowly than the far side. Heat-producing elements like thorium, uranium, and potassium may have preferentially concentrated on the near side during magma ocean solidification. Orbital measurements confirm thorium concentrations are significantly higher in Maria regions than in far-side highlands. These elements kept the near side warmer longer, facilitating prolonged volcanism. The asymmetry is also reflected in impact basins. The far side contains the South Pole Aitken Basin, the moon's largest impact structure at 2,500 kilometers in diameter. Despite its colossal size and the crater penetrating deeply into the crust, this basin did not fill with lava. The crust was simply too thick to permit significant eruptions. Recent studies using seismic data from Apollo missions and modern gravitational measurements revealed that the boundary between crust and mantle is at very different depths in the two hemispheres. This asymmetric discontinuity, called the Mohorovičić discontinuity, confirms the moon has a fundamentally asymmetric internal structure. The dichotomy between lunar hemispheres is not just a visual curiosity. It represents fundamental differences in composition, thermal history, and geological evolution. The near side underwent intense volcanic activity that lasted billions of years. The far side remained geologically quiet, preserving craters from ancient impacts virtually unchanged. This global asymmetry makes the moon unique among large satellites in the solar system. Other satellites show regional variations, but none exhibit such a pronounced hemispheric dichotomy. The moon is not a uniform sphere. It is a world with two distinct faces, each telling a different geological story. And scattered across these two faces are some of the moon's most enigmatic visual features. Bright and sinuous patterns that defy simple explanations. 18. Lunar swirls and their magnetic origins. Why do bright and sinuous patterns exist in certain regions of the lunar surface? These features, called lunar swirls, appear as meandering light bands that stand out dramatically from the surrounding darkened regolith. They are not craters, not lava flows, and have no significant topographic relief. They are simply brightness patterns extending for dozens of kilometers in shapes resembling cream swirls in coffee. The most famous example is Reiner Gamma, located in Oceanus Procellarum. This swirl is approximately 70 kilometers long and shines intensely in orbital images. Its albedo, or reflectivity, is about twice that of the surrounding regolith. The feature is so bright that amateur astronomers with modest telescopes can observe it from Earth. For decades, lunar swirls were mysterious. They did not correspond to any known geological feature. There were no associated craters, no evidence of recent volcanism, and no obvious compositional differences. Then scientists discovered something surprising. Each lunar swirl is associated with a localized magnetic anomaly. These magnetic anomalies create localized magnetic fields up to 300 nanoteslas. Although this is only 1% of Earth's magnetic field strength, it is sufficient to have a measurable effect. The prevailing hypothesis is that these localized magnetic fields protect the surface from solar wind, which normally darkens regolith over time. Solar wind consists of charged particles, mainly protons and electrons, traveling at 400 kilometers per second. When these particles strike unprotected lunar regolith, they cause chemical alterations. Iron atoms and minerals are reduced to nanophase metallic iron. This iron gradually darkens regolith through a process called space weathering. In regions with localized magnetic fields, charged solar wind particles are deflected. Like an invisible magnetic umbrella, the field directs particles around the protected area. Regolith in these protected zones does not undergo space weathering as quickly. It maintains its original lighter color, creating visual contrast with surrounding darkened areas. But this theory does not explain the specific sinuous patterns. Why do protected areas form swirls instead of circular patches? The answer may lie in the three-dimensional geometry of magnetic fields. Magnetic fields are not uniform. They have complex field lines that arc and connect in intricate ways. Computer simulations showed that when solar wind interacts with magnetic fields of complex geometry, it creates correspondingly complex deposition patterns. Deflected particles can be channeled along specific field lines, creating protection bands that follow magnetic contours. These bands correspond to the sinuous patterns observed. Some swirls may have different origins. An alternative theory proposes that ice-rich comets colliding with the Moon at low velocity could deposit volatile materials temporarily. Sublimation of these volatiles could alter the surface properties of regolith. But this theory does not explain the consistent correlation between swirls and magnetic anomalies. Spectral analyses of swirls revealed mineralogical compositions virtually identical to surrounding regolith. There are no detectable significant chemical differences. This confirms swirls are not deposits of different materials. They are the same regolith in a different state of space weathering, preserved by magnetic protection. The age of swirls is difficult to determine. Some may be extremely ancient, dating from when magnetic anomalies formed billions of years ago. Others may be relatively young if magnetic fields changed configuration due to recent impacts. Small impact craters within some swirls show bright edges, suggesting the magnetic protection process is still active. Future missions could land directly on swirls to study them up close. Regolith samples collected inside and outside protected zones would reveal microscopic differences in weathering. High-resolution magnetic measurements would map the three-dimensional structure of fields. This information would help definitively determine the origin of underlying magnetic anomalies. Lunar swirls are visual reminders that the Moon once had a global magnetic field, and that vestiges of that field persist in specific locations. They demonstrate how relatively weak magnetic fields can have observable effects over millions of years. And they are not the only anomalies hidden on the Moon. Beneath the surface, buried deeply below lava plains, exist mass concentrations so dense they affect the orbits of any object passing over them. 19. Gravitational Mascons hidden beneath the surface. Why do spacecraft orbiting the Moon accelerate and decelerate unexpectedly? During Apollo missions, engineers noticed something strange. Satellites in lunar orbit did not follow perfectly predictable trajectories. They slightly accelerated over certain regions and decelerated over others. These orbital variations revealed the existence of mass concentrations buried beneath the surface, known as Mascons. Mascons are regions where the density of subsurface material is significantly higher than average. They create localized gravitational anomalies that can be measured by precise changes in orbital spacecraft velocity. The variations are small, typically a few millimeters per second, but are consistent and repeatable. Modern instruments can map them with extraordinary precision. Most Mascons are located under the Maria, the dark basaltic lava plains. Mare Imbrium, Mare Serenitatis, Mare Crisium, and other major seas all have associated Mascons. The positive gravitational anomalies in these regions are some of the strongest in the solar system for a moon-sized body. What causes these mass concentrations? The explanation involves two related processes. First, the impact basins themselves that eventually filled with lava. When giant asteroids collided with the Moon billions of years ago, they created enormous depressions. These depressions represented significant mass deficits, initially creating negative gravitational anomalies. Then volcanism filled these basins. Basaltic lava flowed into the depressions, piling up in layers up to 1 kilometer thick. Lunar basalt has a density of approximately 3.3 grams per cubic centimeter. This is significantly denser than surrounding regolith or highland rocks, which have densities of 2.8 to 3.0 grams per cubic centimeter. But basalt alone does not completely explain the intensity of Mascons. There must be additional high-density material buried beneath the lava layers. Gravitational models suggest that part of the denser upper mantle may have been uplifted during the impacts that created the basins. This dense material remained relatively close to the surface. Additionally, the weight of thick basalt layers may have compressed underlying material, increasing its density. Over millions of years, gravitational subsidence may have caused isostatic adjustments. The basin floor sank slightly under the basalt's weight, pushing mantle material upward at the basin edges. Mascons significantly affect satellites in low lunar orbits. For long-term missions, accumulated gravitational perturbations can alter orbits sufficiently to cause surface collision. Apollo lunar module missions maintained orbits only for limited periods, partly for this reason. Modern satellites require regular orbital adjustments to compensate for Mascon-caused perturbations. NASA's Grail mission, launched in 2011, mapped the lunar gravitational field with unprecedented precision. Two identical spacecraft flew in formation just 55 kilometers above the surface. By measuring tiny variations in the distance between them caused by gravitational differences, Grail created a gravitational map with resolution of a few kilometers. Grail data revealed complex gravitational structures. Beyond the main Mascons under Maria, the mission detected subsurface intrusion dikes, crustal thickness variations, and buried impact structures. Some ancient impact basins that were completely erased superficially are still detectable through their gravitational signatures. Mascons are not unique to the Moon. Mars also has gravitational anomalies associated with large impact basins. But lunar mascons are particularly pronounced because the Moon has no plate tectonics or significant erosion to redistribute mass over time. Structures created billions of years ago remain essentially frozen. For future crewed missions, understanding mascons is critical for navigation planning. Orbital calculations must incorporate detailed gravitational models to ensure spacecraft maintain stable orbits. Lunar modules need to adjust their descent trajectories to compensate for unexpected accelerations caused by passing over mascons. These buried mass concentrations also provide valuable information about lunar geological history. They preserve records of ancient crustal structure, lava layer thickness, and the depth of original basins before volcanic filling. Mascons are gravitational archives of events that occurred billions of years ago. And buried in the same regions containing mascons are other vestiges of the lunar volcanic past, small colored glass spheres that tell stories of explosive eruptions. 20. Ancient glass beads from volcanic fountains. What are the colored glass spheres discovered on the Moon? During the Apollo 17 mission in 1972, geologist Harrison Schmitt noticed something extraordinary while walking through the Taurus Littrow Valley. An area of regolith glowed with an intense orange color. He collected samples of this orange soil, and later analyses revealed it consisted of tiny volcanic glass spheres, each with diameters of 20 to 45 micrometers. These spheres are not rare. Apollo missions collected volcanic glass samples in multiple colors. Besides the orange from Apollo 17, dark green spheres were found by Apollo 15, and glasses in amber and red tones at other locations. Each color reflects a slightly different chemical composition and a distinct eruptive history. The spheres formed through a process called lava fountain eruption. Magma-rich and volatile gases erupted explosively through fissures in the surface. In low lunar gravity, drops of molten lava were launched dozens or hundreds of meters into the air. During flight, drops cooled rapidly in vacuum, solidifying as perfect glass spheres. Cooling was extremely rapid. Estimates suggest drops solidified within seconds after being ejected. This rapid cooling did not allow crystals to form. The result is amorphous glass with disordered molecular structure. This glass preserves the exact chemical composition of magma at the moment of eruption. Radiometric dating of Apollo 17 orange spheres revealed an age of 3.64 billion years. Apollo 15 green spheres are slightly older, at 3.7 billion years. These ages coincide with a period of intense lunar volcanism. The eruptions occurred hundreds of millions of years after the Moon formed, but billions of years before the present. The presence of glass spheres was surprising for another reason. They contained traces of volatile elements thought to be completely absent from the Moon. Analyses detected small amounts of water, sulfur, fluorine, and chlorine trapped in the glass. Although concentrations are low compared to terrestrial rocks, they prove the lunar interior is not completely dry. Sphere colors are determined mainly by iron and titanium. Orange spheres have high titanium content, approximately 9% by weight. Green ones have less titanium but are iron-rich. These variations indicate different regions of the lunar mantle had distinct chemical compositions when magma formed. Volcanic glass deposits are not limited to Apollo landing sites. Orbital observations identified more than 100 dark pyroclastic deposits scattered across the lunar surface. These deposits appear as dark patches, often surrounding small volcanic craters or fissures. They represent remnants of ancient explosive eruptions. One of the largest known pyroclastic deposits is in Alphonsus, a 119-kilometer diameter crater in the Central Highlands. Dark patches on the crater floor were identified as volcanic glass deposits decades ago. High-resolution telescopic observations revealed these patches extend for dozens of kilometers and have estimated thicknesses of several meters. The lava fountains that created these spheres were fueled by gases dissolved in magma. On Earth, water vapor is the main propellant gas in explosive eruptions. On the Moon, carbon monoxide appears to have played an important role. When magma ascended and pressure decreased, dissolved CO formed bubbles that rapidly expanded, fragmenting magma into microscopic drops. Studying these spheres provides windows into the lunar interior. Because they solidified so rapidly, they preserved magma's chemical composition without significant modifications. Analyses of hydrogen isotopes in trapped water molecules suggest some lunar volatiles may have origins similar to certain types of primitive meteorites. The spheres also have practical interest for future exploration. Thick volcanic glass deposits may be valuable mineral resources. Glass can be melted and molded into structural components. Extraction processes could recover oxygen trapped in the glass structure. Some propose pyroclastic deposits be priority targets for settlement because they represent relatively flat terrain near accessible mineral resources. These tiny colored glass spheres are perfect time capsules. They preserve specific moments of volcanic violence that occurred billions of years ago. Each individual sphere flew through the lunar vacuum for a few seconds before falling back to the surface, where it has remained virtually unchanged since. And while these spheres are buried in solid regolith, something even more tenuous exists above the surface, an atmosphere so thin it is essentially indistinguishable from vacuum. 21. The Moon's thin exosphere and its composition. Does the Moon have an atmosphere? The technical answer is yes, but it is so incredibly tenuous it practically does not exist. The Moon possesses an exosphere, an extremely rarefied atmosphere where molecules rarely collide with each other. The total density is only 100 atoms per cubic centimeter. For comparison, Earth's atmosphere at sea level contains 10^19 molecules per cubic centimeter. This means the lunar exosphere has a density approximately 1 trillion times lower than Earth's atmosphere at sea level. Total pressure is approximately 3 x 10^15 atmospheres. For practical purposes, the lunar surface is in vacuum. Astronauts need pressurized suits because there is virtually no atmospheric pressure. But this tenuous exosphere is still scientifically fascinating. It is constantly replenished by multiple processes and constantly lost to space. It is a dynamic system in delicate equilibrium between sources and escapes. Understanding the lunar exosphere provides insights into processes occurring on all airless bodies in the solar system. The exosphere's composition is surprisingly diverse. Helium, argon, neon, sodium, potassium, and even water molecules have been detected. Each element arrives at the exosphere through different processes. Helium comes mainly from solar wind. Alpha particles, which are helium nuclei, collide with the surface and some are temporarily captured before escaping. Argon has radioactive origin. The argon-40 isotope is a decay product of potassium-40 in lunar rocks. Over billions of years, argon atoms accumulated in interstitial spaces in regolith. When the surface is heated by sunlight or disturbed by meteorite impacts, argon is released and enters the exosphere. Sodium and potassium come from sputtering, the same process that creates the lunar sodium tail. When solar wind ions strike the surface at high velocity, they eject individual atoms from regolith. Sodium and potassium, being relatively light and present in common minerals, are easily released. They become minor but detectable components of the exosphere. The total amount of mass in the lunar exosphere is surprisingly small. Estimates suggest approximately 25,000 kilograms of gases in total. For context, that is less mass than a single loaded truck. Distributed over the entire lunar surface of 38 million square kilometers, it results in the extremely low density observed. The exosphere varies dramatically with lunar position and time of day. During the lunar day, when the surface is illuminated and heated, more atoms are released through thermal desorption. At night, when temperatures drop to 173 degrees Celsius, many atoms condense back to the surface. The exosphere literally freezes to the ground during night. Meteorite impacts provide temporary material injections. When a meteorite strikes the surface, it instantly vaporizes rock and regolith. Some of these vapors escape as temporary clouds of atoms. These clouds dissipate rapidly, But while they exist, they locally increase exospheric density by factors of 10 or more. NASA's Lady mission, which orbited the Moon between 2013 and 2014, detected something unexpected: regular dust spikes in the exosphere that coincided with known meteor showers. When the Moon passed through cometary debris streams, like the Geminids or Perseids, micro-impacts launched dust clouds into the exosphere. This was the first direct confirmation that meteor showers detectably affect the Moon. Water molecules in the exosphere were a surprise. Detected by LAD mission's LAMP instrument, these molecules appear and disappear in patterns suggesting they are released when micro-meteorites strike regions containing buried water ice. Each impact vaporizes a small amount of ice, releasing water temporarily before it recondenses or escapes. The lunar exosphere provides no protection against radiation or micro-meteorites. It does not transport sound. It does not cause weather. But it represents a natural laboratory for studying how planetary surfaces interact with the space environment. Similar processes occur on Mercury, on asteroids, and on the moons of outer planets. The Moon is simply the most accessible place to study them in detail. This phantom atmosphere, so thin it is almost non-existent, still reveals active processes. The Moon is not completely dead. Atoms are constantly ejected, circulate briefly, and then fall back or escape forever. It is an eternal cycle of loss and replenishment that will continue as long as the sun shines and meteorites continue bombarding the lunar surface. And these extreme variations between near-perfect vacuum and solid surface create another extreme phenomenon: temperature oscillations that few places in the solar system can match. 22. Temperature variations of 280 degrees Celsius. How much can temperature vary in a single location? On Earth, even the most extreme deserts experience daily variations of perhaps 40 degrees Celsius between day and night. On the Moon, the lack of atmosphere creates temperature oscillations that are absolutely extreme. A single point on the lunar surface can vary from 173 degrees Celsius during night to 127 degrees Celsius during day. This represents an oscillation of 300 degrees Celsius. These extreme variations occur because the Moon has no atmosphere to distribute heat. On Earth, the atmosphere absorbs heat during the day and redistributes it globally through winds and atmospheric currents. At night, the atmosphere acts as a blanket, retaining heat and preventing temperatures from dropping drastically. The Moon has no such protection. When sunlight strikes the lunar surface directly, it heats the regolith rapidly. Without air to absorb part of the radiation, all solar energy is deposited directly on the surface. Lunar regolith is a poor thermal insulator. The surface layer heats intensely, but heat does not penetrate deeply. Only the first centimeters are affected by temperature oscillations. At night, when the sun sets, there is no atmosphere to retain heat. The surface radiates infrared energy directly into space. Within a few hours after sunset, temperatures plummet. During the long lunar night, which lasts approximately 14 Earth days, the surface cools to temperatures near absolute zero in some regions. The coldest temperatures on the Moon are not in open plains, but at the bottom of permanently shadowed craters near the poles. These locations never receive direct sunlight due to the Moon's minimal axial tilt of only 1.54 degrees. Measurements from the Lunar Reconnaissance Orbiter mission recorded temperatures of 248 degrees Celsius in Hermite Crater. This is colder than Pluto at some moments of its orbit. It is only 25 degrees above absolute zero, the lowest theoretically possible temperature. Under these conditions, any volatile that enters these craters becomes permanently frozen. Water molecules, methane, or carbon dioxide simply do not have enough thermal energy to escape. At the other extreme, the highest temperatures occur at the lunar equator at local noon. When the sun is directly overhead, solar radiation intensity is approximately 400 watts per square meter. Without atmosphere to absorb or reflect part of this energy, all of it heats the surface. In some protected locations where heat can accumulate, temperatures may even exceed 130 degrees Celsius. These oscillations create significant mechanical stresses in lunar rocks. Materials expand when heated and contract when cooled. Repeated cycles of 300-degree variation over billions of years fracture rocks into progressively smaller fragments. This process, called thermal shock, contributes significantly to lunar regolith formation. Apollo astronauts experienced these extreme variations directly. Their spacesuits had to deal with surfaces that could be at 110 degrees Celsius, where sunlight struck directly, while areas in shadow remained at 150 degrees Celsius. The suits incorporated multiple insulating layers and active cooling systems to keep astronauts comfortable. Equipment left on the lunar surface also suffers. Scientific instruments installed by Apollo missions were designed to survive these extremes, but eventually all failed. Thermal cycles degrade seals, fracture electronic components, and cause mechanical failures. The lunar thermal environment is incredibly hostile to technology. Just a few centimeters below the surface, temperatures stabilize dramatically. At approximately 1 meter depth, temperature remains constant around 35 degrees Celsius, regardless of whether it is day or night on the surface. This subsurface thermal stability makes natural tunnels and lava tubes attractive targets for future lunar habitats. Future lunar bases will need sophisticated thermal protection. Surface structures will face enormous challenges dealing with oscillations. Partially buried habitats or those located in natural caves will benefit from subsurface thermal stability. Construction materials will need to withstand extreme thermal cycles without significant degradation over decades. These extreme temperature variations make the Moon one of the most hostile environments in the solar system for sustained operations. But among the challenges the lunar surface presents, there are also valuable clues about solar system history. Some of these clues literally fell from the lunar sky and arrived here on Earth. 23. Ancient lunar meteorites discovered on Earth. How did pieces of the Moon reach Earth? It seems unlikely that lunar rocks could travel 384,000 kilometers through space and land on our planet. But that is exactly what happens. Asteroid impacts on the Moon occasionally eject fragments with sufficient velocity to escape lunar gravity. Some of these fragments eventually collide with Earth as meteorites. By 2025, more than 600 confirmed lunar meteorites have been found on our planet. These lunar meteorites are scientifically precious. They come from moon locations never visited by Apollo missions or Soviet Luna probes. While Apollo missions collected samples from only 6 locations in the near hemisphere, lunar meteorites potentially represent material from anywhere on the lunar surface. How do scientists identify a meteorite as lunar? The key lies in chemical and isotopic composition. Lunar rocks have distinctive chemical signatures. They are extremely poor in volatile elements and water. The ratio of oxygen isotopes is identical to Apollo samples, but different from Martian meteorites or from asteroids. Specific minerals like pyroxferroite are rare on Earth but common on the Moon. The first lunar meteorite was identified in 1982 in Antarctica. Japanese researchers collected a 31-gram fragment called Yamato 791197. Initial analyses showed it was an orthosite, a rock type common in lunar highlands but rare on Earth. Chemical composition did not match any known meteorite. Comparisons with Apollo samples confirmed its lunar origin. Since then, Antarctica has become the most productive location for finding lunar meteorites. White ice provides perfect contrast for dark rocks. Glaciers concentrate meteorites in certain regions called meteorite traps. Research teams systematically traverse these areas, collecting any rock they find. Approximately 60% of known lunar meteorites were found in Antarctica. Hot deserts are the second best place to find meteorites. The Sahara, Arabian Peninsula, and Australian desert have produced numerous lunar meteorites. In arid terrains, rocks are easily visible. Lack of vegetation and slow erosion preserves meteorites for thousands of years. Professional and amateur meteorite hunters scour these regions searching for space fragments. How long do lunar meteorites take to reach Earth? Orbital calculations suggest most take between 10,000 and 1 million years. After being ejected from the Moon, fragments enter elliptical orbits around the Sun. These orbits eventually cross Earth's orbit. When Earth passes the crossing point at the right moment, the fragment is captured by terrestrial gravity and falls as a meteorite. Some lunar meteorites contain information Apollo samples did not provide. A meteorite called Northwest Africa 032, found in Algeria, contains very young basalt dated at only 2.8 billion years. This is several hundred million years younger than the most recent basalts collected by Apollo missions. This proves lunar. Volcanism continued later than Apollo samples suggested. Another meteorite, Dhofar 025 found in Oman contains breccia, with fragments of multiple lunar rocks. Analyses revealed components with ages ranging from 2.8 to 3.9 billion years. This single meteorite provides samples of multiple geological events that occurred over billions of years of lunar history. It is like a condensed geological archive in a single 750-gram fragment. The largest known lunar meteorite weighs 1,814 grams. Called Dar al-Ghani 400, it was found in Libya in 1998. Its relatively large mass suggests it came from a particularly powerful impact. Most lunar meteorites weigh less than 100 grams. Smaller fragments are more easily ejected with escape velocity. Estimating how many lunar meteorites fall on Earth annually is difficult. Most fall in oceans or inaccessible regions and are never found. Models suggest approximately 1,000 to 2,000 kilograms of lunar material reaches Earth each year. But only a minuscule fraction is recovered. Finding a lunar meteorite requires luck, knowledge, and effort. The scientific value of these meteorites is enormous. They cost a fraction of what sample return missions would cost, but provide material from unvisited locations. Future analyses with increasingly sensitive techniques will continue extracting information from these space rocks. And each lunar meteorite helps answer a fundamental question that intrigued scientists for decades. Exactly when and how did the moon form? 24. The moon's age and formation. Timeline. When exactly was the moon born? Determining the moon's precise age was one of the most important scientific objectives of Apollo missions. Lunar rock samples allowed scientists to apply radiometric dating techniques to establish a definitive timeline. The answer transformed our understanding not just of the moon, but of the entire primitive solar system. The moon is approximately 4.51 billion years old. This age was determined through analyses of anorthositic rocks from lunar highlands collected by Apollo missions. Earth is 4.54 billion years old. This means the moon formed only 30 to 50 million years after Earth's formation. In geological terms, this is almost simultaneously. This temporal proximity strongly supports the giant impact theory. If the moon had formed independently and been captured by terrestrial gravity, its age could be significantly different. If it had separated from a rapidly rotating Earth, it would be as old as our planet. The 30 to 50 million year difference corresponds to the time necessary for primitive Earth to accumulate sufficient mass for the giant impact to occur. Radiometric dating works by measuring the abundance of radioactive isotopes and their decay products. Uranium-238 decays to lead-206 with a half-life of 4.47 billion years. Samarium-147 decays to neodymium-143 with a half-life of 106 billion years. By comparing the proportions of these isotopes in lunar minerals, scientists calculate how much time has passed since the rock solidified. The oldest rocks returned from the moon are highland anorthosites. These anorthosites crystallized from the global magma ocean that covered the moon immediately after its formation. Light minerals like plagioclase floated to the magma ocean surface, accumulating in thick layers. When these layers solidified, they formed the primitive anorthositic crust. Dating these samples indicates the lunar crust solidified between 4.51 and 4.36 billion years ago. The magma ocean took approximately 150 million years to solidify completely. During this period, the moon transitioned from a sphere of molten rock to a body with differentiated solid crust, mantle, and core. Maria basalts are much younger. The oldest basalt samples are approximately 4.0 billion years old. The youngest are about 3.0 billion years old. Lunar meteorites found on Earth revealed even younger basalts, with ages up to 2.8 billion years. This indicates lunar volcanism continued sporadically for more than 1.5 billion years. The lunar formation timeline can be reconstructed thus. 4.51 billion years ago, the giant impact occurs. In the first days after impact, ejected material forms a disk around Earth. The moon accretes from this disk in 10 to 100 years. The newly formed moon is covered by a magma ocean hundreds of kilometers deep. Over the next 100 to 200 million years, the magma ocean cools and solidifies. Dense minerals sink, forming the mantle. Light minerals float, forming the crust. The metallic core, if not already formed, separates and sinks to the center. By around 4.3 billion years ago, the Moon has completely differentiated internal structure. Between 4.1 and 3.8 billion years ago, the late heavy bombardment occurs. Asteroids and comets collide with the Moon at extremely high rates. The largest impacts create the giant basins that will eventually become the Maria. These impacts deeply fracture the crust and heat the interior. Between 3.8 and 3.0 billion years ago, volcanism fills impact basins with basaltic lava. Eruptions gradually decrease as the lunar interior cools. By around 3.0 billion years ago, volcanism largely ceases. Isolated eruptions may have continued until 1 or 2 billion years ago, but the Moon's geologically active era essentially ended. Since then, the Moon has been geologically inactive. Only meteorite impacts have significantly altered the surface. Regolith developed through billions of years of micro-meteorite bombardment. But the main features we see today were established more than 3 billion years ago. This timeline shows the Moon underwent dramatic changes in its first 1.5 billion years. It formed, melted, solidified, was intensely bombarded, and experienced extensive volcanism. After that, changes practically stopped. The moon Neil Armstrong stepped on in 1969 was essentially the same moon that existed when dinosaurs walked Earth. And this long-term geological stability ensures the Moon will remain a world without something that defines dynamic planets. Weather. 25. Why the Moon will never have weather. Why is the Moon immune to climate variations that affect other worlds? On Earth, weather is a constant concern. Storms, cold fronts, heat waves, and seasonal changes dominate our lives. Even Mars has dust storms covering entire planets, but the Moon has never experienced and will never experience weather phenomena. The fundamental reason is simple. The Moon has no significant atmosphere. Weather requires an atmosphere. Winds, clouds, precipitation, and storms are atmospheric phenomena. They occur when air masses move, when water vapor condenses, and when pressure differences create gradients. On the Moon, atmospheric pressure is 3×10 or 15 atmospheres. This is essentially vacuum. There is not enough air to create any meteorological phenomenon. Even if the Moon had atmosphere, the lack of rapid rotation would eliminate many climate processes. On Earth, 24-hour rotation creates the Coriolis effect, which organizes weather systems into circular patterns. Hurricanes spin, jet streams flow, and weather fronts move due to rotation. The Moon rotates once every 27.3 days. This slow rotation would not generate the complex atmospheric circulation patterns we see on Earth. Heat distribution would be completely different. On Earth, atmosphere and oceans redistribute heat from equatorial regions to the poles. Ocean currents like the Gulf Stream transport enormous amounts of thermal energy. Atmospheric winds equalize temperatures between day and night. On the Moon, without atmosphere or oceans, there is no heat redistribution mechanism. This results in the thermal extremes discussed earlier. The daytime side reaches 127 degrees Celsius, while the nighttime side drops to 173 degrees Celsius. If the Moon had atmosphere, these extremes would be dramatically reduced. The atmosphere would absorb heat during the day and radiate it during night, stabilizing temperatures. The Moon also has no hydrological cycle. On Earth, water evaporates from oceans, forms clouds, precipitates as rain or snow, and returns to oceans through rivers. This cycle drives much of our weather. Humidity in the atmosphere absorbs and releases heat, fueling storms. On the Moon, any surface water would instantly sublimate in vacuum. There is not enough pressure to maintain liquid water. Even in a distant past, when the Moon may have had a temporary atmosphere of volcanic gases, that atmosphere was never thick enough to create weather comparable to Earth's. The Moon's weak gravity, only 1/6 of Earth's, means atmospheric gases escape easily. Lunar escape velocity is only 2.38 kilometers per second compared to 11.2 kilometers per second for Earth. Gas molecules in the atmosphere have average velocities determined by temperature. For light gases like hydrogen and helium, a significant fraction of molecules reach velocities above escape velocity. These molecules simply fly into space. Over millions of years, even heavier gases are gradually lost. The lack of a global magnetic field aggravates atmospheric loss. On Earth, the magnetic field deflects solar wind, protecting the atmosphere. On the Moon, solar wind strikes the exosphere directly. Charged particles collide with atmospheric atoms, transferring energy and ejecting them into space. This process, called sputtering, continuously removes atmosphere. Venus, despite having only a weak magnetic field, maintains a thick atmosphere because it has strong gravity and constantly replenishes gases through volcanism. Mars lost much of its atmosphere after its magnetic field died, but maintains a thin atmosphere because it has reasonable gravity. The Moon has weak gravity, no magnetic field, and no active volcanism. It is the perfect combination to remain without atmosphere. This means the lunar surface is eternally exposed to vacuum and direct radiation. There is no ultraviolet ray filtration, no protection against high-energy particles, and no thermal moderation. Each lunar day, lasting 29.5 Earth days, brings the same extreme conditions. There are no weather surprises, no seasonal variability, and no climate change. For future colonists, this has advantages and disadvantages. The advantage is total predictability. Engineers know exactly what conditions to expect. There are no storms that could damage equipment or delay operations. The disadvantage is there are no atmospheric resources. No oxygen to breathe, no nitrogen for fertilizers, and no radiation protection. The Moon is and always will be a world without weather, frozen in a state of permanent vacuum. But this same absence of atmosphere has perfectly preserved geological features that on Earth would have been eroded billions of years ago. And among these preserved features are openings leading to hidden worlds beneath the surface. 26. Natural caves discovered by probes. What exists below the lunar surface besides solid rock? For decades, scientists speculated about the possibility of natural caves on the Moon. Then, in 2009, the Japanese Kaguya probe photographed something extraordinary, a perfectly circular hole. 65 meters in diameter on the floor of Marius Hills. Later analyses revealed this pit was not just a shallow crater. It was a vertical opening descending at least 80 meters to an underground structure. This discovery confirmed decades of speculation. The Moon has natural caves, and many of them are accessible through vertical pits on the surface. Since 2009, more than 200 pits have been identified by multiple orbital missions. They vary in size from 5 to 900 meters in diameter. Most are located in Maria regions, the basaltic lava plains. These pits are probably openings to lava tubes, the same tunnels discussed earlier. When lava flowed beneath the surface billions of years ago, it created extensive tunnels. Most of these tunnels remained intact, but in some locations, the roof partially collapsed. These collapses created the openings we observe today as lunar pits. NASA's Lunar Reconnaissance Orbiter mission investigated these pits in detail. Its high-resolution camera captured images showing the inner walls of pits. Some images revealed pits open into larger cavities underneath. In at least one case, the cave under the pit appears to extend horizontally beyond what cameras can see. The Marius Hills pit is one of the most intriguing. Ground-penetrating radar measurements suggested the lava tube below this pit may be 50 kilometers long and several hundred meters wide. If these dimensions are confirmed, it would be an underground structure larger than any known cave on Earth, a space large enough to house an entire city. Another notable pit is in Philolaus crater near the lunar North Pole. This pit is approximately 50 meters in diameter and was photographed at angles revealing part of the interior. Images show the pit floor is covered with loose regolith that apparently fell from the ceiling over millions of years. This suggests the structure is at least several dozen meters deep. Temperatures inside these pits are surprisingly stable. While the lunar surface oscillates between 173 and 127 degrees Celsius, infrared thermal measurements of pits revealed consistent temperatures of approximately 17 degrees Celsius. This is close to room temperature on Earth. The explanation is that pits access the stable subsurface thermal zone where diurnal oscillations do not penetrate. This thermal stability makes pits and connected caves extraordinarily attractive for human exploration. Habitats built inside lava tubes would not need heating during night or cooling during day. The naturally moderate temperature would drastically reduce energy requirements. Colonists could live in environments with minimal thermal variations. Caves also provide radiation protection. The lunar surface is constantly bombarded by galactic cosmic radiation and solar flares. Astronauts on long-duration missions would need substantial shielding. Rocks are excellent shielding, just a few meters of solid basalt block virtually all harmful radiation. Lava tubes provide this protection naturally. Protection against micro-meteorites is another benefit. The lunar surface is constantly struck by high-velocity particles. There is no atmosphere to burn them before impact. Surface structures would need shielding against perforation. Caves completely eliminate this risk. Solid rock walls are impervious to anything smaller than a large meteorite. But exploring these caves presents significant technical challenges. Pits have steep or vertical walls. Descending 80 meters in low lunar gravity with equipment is possible, but requires careful planning. Conventional rovers cannot access these structures. Proposed missions include flying drones, rovers with rappelling capability, or even small satellites that could slowly descend using propulsion. NASA and other space agencies are developing mission concepts specifically for lunar cave exploration. One proposal involves a rover that would position itself at a pit's edge and launch small drones equipped with cameras and LiDAR. These drones would map the interior three-dimensionally before any crewed mission was attempted. These natural caves represent some of the most promising environments for permanent human settlement on the Moon. They provide protection, thermal stability, and potentially access to mineral resources exposed in their walls. Decades before surface lunar cities are viable, the first lunar communities may thrive hidden in ancient tunnels created by lava rivers billions of years ago. 27. The mysterious lunar horizon glow. Why did Apollo astronauts see bright light on the lunar horizon before sunrise? During multiple missions, crew members orbiting the Moon reported strange observations. While passing over the night side, they saw a tenuous, whitish glow hovering just above the lunar horizon. This phenomenon, called lunar horizon glow, appeared a few minutes before sunrise and persisted after sunset. The glow was not a result of Earthlight reflection. It appeared even when Earth was not visible. It was not starlight or equipment reflection from the spacecraft. Astronauts described it as a diffuse luminescence extending 10 to 20 degrees above the horizon. It was faint, but distinctly visible against the black sky of space. The most probable explanation involves levitated lunar dust. The Moon's surface is covered by extremely fine regolith particles. These particles range in size from 40 to 800 micrometers and are electrically charged by solar radiation and solar wind. During the lunar day, ultraviolet light from the sun ejects electrons from dust particles, giving them positive charge. At night, when the surface is not exposed to sun, electrons from solar wind plasma are absorbed by particles, giving them negative charge. In the terminator region, the line between day and night, extreme charge differences exist over very short distances. These differences create intense electric fields. These electric fields can be strong enough to lift dust particles. Simulations calculate that fields of hundreds to thousands of volts per meter can develop at the terminator. Particles smaller than 10 micrometers in diameter can be levitated to heights of meters or even dozens of meters above the surface. When these suspended particles are illuminated by sunlight that still reaches elevated altitudes even after sunset on the surface, they scatter light. It is similar to how dust in Earth's atmosphere creates twilight. The difference is that on the Moon there is no atmosphere. Light is being scattered exclusively by electrostatically levitated dust particles. Surveyor 7, which landed on the Moon in 1968, provided direct evidence. Its camera captured images showing diffuse rays of light above the horizon after sunset. Images showed vertically elongated beams, consistent with columns of suspended dust scattering sunlight. The Lunar Ejecta and Meteorites experiment mission, placed on the surface by Apollo 17, attempted to measure levitated dust directly. Sensors detected moving particles at altitudes up to 30 centimeters above the surface. Readings increased dramatically during lunar sunrise and sunset, exactly when electric fields at the terminator would be strongest. More recent observations from the LED mission confirm the presence of dust in the lunar exosphere. Its dust detectors registered particles at orbital altitudes. Although density was extremely low, the constant presence of dust at these altitudes suggests some processes launching material from the surface. The amount of dust involved is minuscule. Estimates suggest concentrations of only a few particles per cubic meter at altitudes of a few meters. But because the lunar horizon is visible for dozens of kilometers, the cumulative scattering effect through this volume is sufficient to create detectable glow. Meteor showers can intensify the phenomenon. When micro-meteorites strike the surface, they launch dust clouds that can remain temporarily suspended. Observations during known meteor showers showed increases in horizon glow, supporting this connection. This mysterious horizon glow is not just a visual curiosity. It represents an active dynamic process on the moon. Dust is constantly being moved, suspended, and redistributed by electrostatic forces. This has implications for surface equipment that may be covered by migrating dust, and for astronaut health who may inhale suspended particles. And this dust that creates horizon glow has an extraordinarily long history, preserving records of processes that began when the solar system was young. 28. Regolith with 4.5 billion years of history. How long does it take to form lunar soil? The regolith covering the moon's surface did not form in millions of years. It took billions of years of constant bombardment to pulverize solid rocks into a layer of fine dust and fragments. This layer varies from a few meters thick in young Maria plains to 10 or 15 meters in ancient highlands. Lunar regolith is fundamentally different from terrestrial soil. On Earth, soil is a product of erosion by water, wind, and biological processes. It contains organic matter, chemically altered minerals, and structure created by plant roots. Lunar regolith has never been touched by liquid water or living organisms. It is exclusively a product of impacts and radiation. The process begins with micro-meteorites. The moon is constantly bombarded by particles ranging from dust grains to fist-sized rocks. There is no atmosphere to burn them up. Each particle strikes the surface at velocities of 11 to 72 kilometers per second. These extreme velocities transform even tiny particles into devastating projectiles. When a micrometeorite strikes, it does not simply perforate the surface. Kinetic energy is so high that both the projectile and target material are instantly vaporized. A microscopic crater forms. Ejected material is launched in ballistic arcs, falling back at varying distances. Each impact fractures, pulverizes, and redistributes material. Over billions of years, this process called impact gardening has completely mixed the first meters of the lunar surface. Individual particles have been impacted, buried, re-exposed, and impacted again countless times. Regolith is a thoroughly homogenized mixture of fragments from multiple sources. The gardening rate varies with depth. The first millimeters are completely overturned in approximately 1 million years. The top 1 centimeter layer is completely mixed in about 10 million years. But mixing the first complete meter takes approximately 100 million years. The deepest regolith layers contain material that has not been disturbed for hundreds of millions of years. Analyses of Apollo samples revealed regolith contains fragments of multiple ages. A single handful can include impact glass formed 3 billion years ago, basalt fragments from 3.5 billion years ago, and highland anorthosite from 4.4 billion years ago. It is a completely shuffled geological archive. But regolith also records history in a unique way. Individual mineral grains exposed on the surface capture solar wind particles. Over millions of years, atoms of hydrogen, helium, and other elements are implanted in the first nanometers of each grain. These grains are eventually buried by impact gardening. By analyzing the depth of solar wind implantation in grains from different layers, scientists can estimate how long each grain spent exposed on the surface. Studies showed typical grains spend between 1 and 10 million years on the active surface before being buried. Some grains show multiple exposures indicating they were buried and re-exposed several times. Regolith also contains microscopic glass spherules called impact spherules. These microscopic spheres formed when drops of melted rock were launched from impact craters and solidified during flight. Some spherules are only micrometers in diameter. Billions of them are mixed in each kilogram of regolith. Regolith particles are coated with a nanometer-thick layer of impact glass. This layer, called space patina, forms when vapors from microscopic impacts condense on nearby grains. Patina thickness increases with exposure time. Grains with thicker patinas have been exposed on the surface longer. Rare elements called solar noble gases provide another form of dating. Helium-3, neon-20, and argon-36 from solar wind accumulate in regolith over time. By measuring concentrations of these isotopes, scientists estimate how long regolith has been exposed to solar wind. Some samples show exposures of more than 100 million years. Regolith is not just passive dust. It is a dynamic archive preserving billions of years of meteorite bombardment, solar wind exposure, and space weathering processes. Each grain tells a story, and that story includes exposure to radiation levels that would make the lunar surface lethal for unprotected life. 29. Intense radiation on the lunar surface. How much radiation strikes the lunar surface? Apollo astronauts faced radiation environments that were orders of magnitude more intense than anything experienced on Earth. Without atmosphere or magnetic field for protection, the lunar surface is bombarded by galactic cosmic radiation, solar flares, and high-energy particles. The radiation dose accumulated in 1 week on the Moon equals approximately 1 year on the International Space Station. Radiation comes from 3 main sources. First, galactic cosmic rays. These are atomic nuclei accelerated to speeds near light speed by supernovas and other violent cosmic events. They traverse the solar system constantly. On Earth, the atmosphere absorbs them. On the Moon, they strike the surface directly. The second source is solar particle events. When the Sun produces solar flares or coronal mass ejections, it launches high-energy protons and electrons into space. During intense solar events, particle flux can increase by factors of 100 or more. These events are unpredictable and potentially lethal for unprotected astronauts. The third source is secondary radiation. When high-energy particles strike the lunar surface, they interact with atoms in regolith. These interactions produce secondary neutrons, X-rays, and other particles. These secondary particles can be as harmful as primary radiation. An astronaut on the lunar surface is effectively bombarded from above by primary radiation and from below by radiation reflected from the ground. Radiation dose is measured in sieverts. 1 sievert represents exposure sufficient to significantly increase cancer risk. Nuclear power plant workers on Earth are limited to 50 millisieverts per year. Astronauts on the lunar surface would receive approximately 380 millisieverts per year from galactic cosmic radiation alone. During solar particle events, dose rates skyrocket. A Class X solar flare, the most intense type, can deliver doses of hundreds of millisieverts in a few hours. If astronauts were performing a lunar walk during such an event without adequate protection, they could receive lethal doses before returning to the module. Apollo missions were lucky. None occurred during major solar particle events. But between Apollo 16 and 17 missions in August 1972, a massive solar flare occurred. If astronauts had been on the lunar surface during that event, they could have received fatal radiation doses. The time window was a matter of months. Instruments left on the Moon by Apollo missions measured radiation continuously for years. Data confirmed the lunar surface experiences an extremely hostile radiation environment. There are no safe periods. Galactic cosmic radiation is constant. Solar events are unpredictable but common enough to represent a serious threat. For long-duration missions, radiation protection is a critical challenge. Water is excellent shielding, absorbing both charged particles and neutrons. Lunar. Regolith also works. Approximately 2.5 meters of regolith reduce radiation dose by 50%. 5 meters reduce it by more than 90%. Lunar habitats will likely be partially buried or covered with regolith. Some proposals suggest using 3D printers to build structures directly with lunar regolith, incorporating shielding into the architecture itself. Other proposals involve inflating habitats and covering them with stacked regolith bags. Natural lava tubes provide ideal protection. Even a few meters of solid rock block practically all harmful radiation. Astronauts living in lava tubes would experience radiation doses comparable to or lower than Earth's. This makes lunar cave exploration a priority for long-term settlement. Radioprotective drugs are being developed. These compounds increase the body's ability to repair DNA damage caused by radiation. But drugs alone are not sufficient. Physical shielding is essential for significant radiation dose reductions. Intense radiation on the lunar surface represents one of the most serious barriers to prolonged human exploration. Unlike engineering challenges that can be solved with better technology, radiation is fundamental physics. It cannot be turned off or avoided. It can only be blocked with sufficient mass between astronauts and space. And this radiation has bombarded not just small areas but giant structures that permanently scar the lunar face. 30 impact craters, 2,500 kilometers in diameter. How large are the biggest impact scars on the Moon? The South Pole Aitken Basin is not just large, it is one of the largest confirmed impact structures in the entire solar system. At 2,500 kilometers in diameter, it extends from the lunar South Pole to Aitken Crater in the southern hemisphere. If this basin were on Earth, it would cover the distance from Lisbon to Moscow. The depth of this basin is equally impressive. The floor is approximately 8 to 13 kilometers below the surrounding highlands. For comparison, Mount Everest is 8.8 kilometers above sea level. You could place Everest inside the South Pole Aitken Basin, and it would not reach the rim. The structure contains enough volume to hold all of North America's Great Lakes multiplied by 10. The impact that created this basin was catastrophic on a planetary scale. Computer models suggest the asteroid was between 150 and 200 kilometers in diameter. It collided with the Moon at velocities of 15 to 25 kilometers per second. The energy released was equivalent to millions of hydrogen bombs exploding simultaneously. The impact penetrated deep into the lunar crust and possibly the upper mantle. Spectral evidence from China's Chang'e 4 mission revealed minerals consistent with mantle material exposed on the basin floor. Olivine and low-calcium pyroxene in specific proportions suggest the impact excavated material from at least 60 kilometers depth. When the asteroid struck, it instantly vaporized both itself and the target material. A fireball of vaporized rock expanded at thousands of degrees Celsius. Shockwaves propagated through the entire Moon. At the point exactly opposite the impact, these waves would converge, potentially fracturing the surface and creating chaotic terrain. Ejected material was launched across the entire lunar hemisphere. Fragments ranging from dust grains to building-sized boulders flew through the lunar vacuum. Some fragments reached escape velocities and left the Moon completely. Others fell back, creating secondary craters thousands of kilometers away. The original basin was even deeper than what we see today. Over hundreds of millions of years, the basin floor rose through a process called isostatic rebound. Dense mantle material below the basin, being lighter than the overlying crust that was removed, slowly pushed upward. This gravitational adjustment reduced basin depth by several kilometers. The age of the South Pole Aitken Basin is estimated at 4.3 billion years. This makes it one of the Moon's oldest features. It formed during the period of intense bombardment that characterized the first 500 million years of the solar system. At that time, asteroids and planetesimals remaining from planetary formation still wandered in abundance. Other giant basins on the Moon include Imbrium, Serenitatis, and Orientale. The Imbrium Basin is 145 kilometers in diameter. The impact that created it 3.85 billion years ago was so powerful that its effects were detected globally. Apollo samples collected 2,500 kilometers away contain material ejected from this single event. The Oriental Basin, 930 kilometers in diameter, is one of the Moon's best preserved impact structures. It formed approximately 3.8 billion years ago and exhibits multiple concentric rings. These rings are faults created when the crust collapsed after the initial impact. Counting and mapping these rings helps scientists understand the mechanics of giant impacts. Impact basins of this scale do not just create depressions. They fundamentally reorganize crustal structure. They thin the crust, deeply fracture the substrate, and alter thermal flow from the interior. These changes influenced where and when subsequent volcanism would occur. Basins became preferential locations for lava eruptions billions of years later. Studying these giant craters provides insights into processes that shaped not just the Moon but all rocky planets. Earth was struck by equally large impactors during the same period. But erosion, plate tectonics, and volcanism erased those ancient scars. The Moon preserves the intact record, and these massive basins not only altered lunar topography, but also created permanent variations in the gravitational field that affect everything in orbit. 31. The Moon's irregular gravitational field. Why does lunar gravity vary from place to place? Gravity on the lunar surface is not uniform. It varies by small percentages depending on where you are. These variations are caused by differences in mass distribution beneath the surface. Regions with denser buried material exert slightly stronger gravitational pull. Average gravity on the lunar surface is 1.62 meters per second squared. This is approximately 16.5% of Earth's gravity. But in some locations over Mascons, gravity can be 0.5% stronger. In other locations, over highlands or subsurface voids, it can be 0.5% weaker. For humans, these differences are imperceptible. For spacecraft in orbit, they are critical. NASA's GRAIL mission mapped the lunar gravitational field with extraordinary precision between 2011 and 2012. Two identical spacecraft flew in formation 55 kilometers above the surface. They maintained constant distance while orbiting. When one spacecraft passed over a gravitational anomaly, it slightly accelerated or decelerated. This changed its distance from the second spacecraft. By measuring these changes with micrometer precision using radio waves, GRAIL created a gravitational map with resolution of a few kilometers. The map revealed structures never seen before. Ancient magma dikes buried beneath the surface appeared as lines of slightly increased gravity. Faults and fractures appeared as zones of reduced gravity. The strongest gravitational anomalies are associated with Maria. These basaltic lava plains have Mascons, mass concentrations that create localized gravitational pulls. Mare Imbrium has a Mascon with an anomaly of approximately Pashu 200 milligaules. A milligoule is 1,000th of Earth's standard gravitational acceleration. But GRAIL also discovered linear high-gravity structures connecting different impact basins. These structures are interpreted as intrusion dikes, pathways where magma flowed through crustal fractures without reaching the surface. Some of these dikes are hundreds of kilometers long and maybe up to 5 kilometers wide. The Moon's far side has a significantly more irregular gravitational field than the near side. Far side highlands contain small-scale gravitational variations reflecting complex topography and overlapping impact structures. The South Pole Aitken Basin, despite its size, has no associated strong Mascon. This suggests it was never filled with significant volumes of dense lava. These gravitational irregularities have important practical consequences. Satellites in low lunar orbits experience constant perturbations. Over weeks or months, these perturbations accumulate and can significantly alter the orbit. Without regular corrections, satellites eventually collide with the surface. Apollo missions experienced these effects directly. The command and service module in lunar orbit needed frequent adjustments to maintain altitude. Trajectory calculations for the lunar module descending to the surface had to incorporate known gravitational anomalies. Errors could result in landings at unplanned locations or even collision. Future missions will use detailed gravitational maps from GRAIL for precise navigation planning. Guidance software will incorporate high-resolution gravitational models. This will enable more precise landings and more stable orbits for long-duration satellites. Gravitational variations also inform geological science. Regions with anomalous gravity indicate buried structures not visible on the surface. Identifying these structures helps scientists reconstruct lunar geological history. Magma dikes reveal where volcanism attempted to reach the surface. Voids indicate where lava tubes or caves exist. The Moon's irregular gravitational field is a signature of its complex history. Each anomaly represents a geological event, an ancient impact, a magma intrusion, a basaltic lava flood, or a crustal fault. Gravity is the invisible memory of billions of years of processes that shaped our natural satellite. And this same weak gravity that creates challenging orbits also explains why lunar topography has fundamental limits on its verticality. 32. Why there are no really high mountains on the Moon. Why are lunar mountains relatively modest? Earth has Mount Everest at 8.8 kilometers above sea level. Mars has Olympus Mons at an astounding 21 kilometers height. The Moon, despite having no erosion that would wear down mountains, has no mountain above 10 kilometers. The tallest lunar mountain, Mons Huygens, is only 5.5 kilometers. The reason lies in the fundamental physics of how tall a mountain can grow before collapsing under its own weight. A mountain's maximum height is determined by rock strength and local gravity. On Earth, basaltic rock can withstand approximately 3x 10^8 pascals of compressive stress before fracturing. Earth's gravity of 9.8 meters per second squared limits mountains to approximately 10 kilometers height before the base begins to flow plastically. On the Moon, gravity is only 1.62 meters per second squared. This is 16.5% of Earth's gravity. With weaker gravity, you would expect mountains could be much taller before collapsing. Theoretically, lunar mountains could reach heights of 60 kilometers before stress at the base exceeded rock strength. But no lunar mountain approaches this theoretical limit. Why? The answer lies in how mountains form. On Earth, mountains grow primarily through plate tectonics. When continental plates collide, crust is compressed, folded, and pushed upward. The Himalayas continue growing today as the Indian plate pushes the Eurasian plate. The Moon has no plate tectonics. Its crust solidified more than 4 billion years ago and has remained rigid since. There are no plate movements to compress and elevate material. Lunar mountains are mainly edges of ancient impact craters or rings of giant impact basins. Mons Huygens, the Moon's tallest mountain, is part of the Montes Apenninus. This mountain range forms the southeast rim of the Imbrium Basin. It is not a volcanic or tectonic mountain. It is ejected material and deformed crust from the impact that created Imbrium 3.85 billion years ago. The peak is simply the highest edge of the crater ring. Mars has much taller mountains because it has recent active volcanism. Olympus Mons is a shield volcano that grew through repeated eruptions over hundreds of millions of years. Martian gravity of 3.7 meters per second squared, 38% of Earth's, allows volcanic structures to grow much taller before collapsing. The Moon had volcanism, but lunar volcanoes were different. Instead of building tall mountains, lunar eruptions produced low-viscosity lava flows that spread in vast sheets. There was no significant vertical construction. The modest shield volcanoes that formed are only a few hundred meters tall. The Moon's most prominent mountains are central peaks in some impact craters. When large asteroids strike the surface, the initial crater floor collapses and then rebounds, creating a central peak. Tycho crater has a central peak approximately 2 kilometers high. Copernicus crater has a 1.2 kilometer peak. These central peaks form within seconds after impact. Molten and fractured rock is thrown upward by the rebound of the crater floor. The peak quickly solidifies into a steep mountain form. But even these peaks rarely exceed 2 to 3 kilometers height. The absence of erosion on the Moon preserves mountains but also prevents their growth. On Earth, sediments eroded from mountains can be subducted and recycled, eventually forming new mountains elsewhere. This cycle allows dramatic topography to regenerate. On the Moon, there is no cycle. Mountains formed billions of years ago remain virtually unchanged, but no new ones form. Future lunar colonists will have relatively flat terrain compared to Earth. This facilitates construction and transportation. There are no mountain ranges comparable to the Andes or Himalayas blocking travel routes. The most significant elevation variations are the rims of impact basins, which can have steep walls but are not mountains in the traditional sense. The Moon's modest mountains are reminders that despite its dramatic appearance in photos, the Moon is geologically dead. Without tectonics, without active volcanism, and without mountain-building processes, lunar topography is entirely a product of impacts and ancient gravitational collapse. What we see today is a landscape frozen in time, shaped almost entirely more than 3 billion years ago. 33. Helium-3. The future fuel hidden on the Moon. Why is lunar helium-3 worth trillions of dollars? This rare isotope, practically non-existent on Earth, is distributed across the entire lunar surface in quantities that could revolutionize energy production. While Earth contains only a few hundred kilograms of helium-3 in its entire atmosphere, the Moon may have more than 1 million tons incorporated in the regolith. This single resource has become the focus of interest for space agencies and private companies. Helium-3 is a helium isotope with 2 protons and only 1 neutron. On Earth, it is extremely rare because our planet formed with little of it, and the magnetic field blocks solar wind, the primary source. On the Moon, without magnetic field or atmosphere, solar wind has directly bombarded the surface for billions of years. Protons from solar wind react with oxygen in regolith, but helium-3 atoms are simply implanted in the first meters of soil. The average concentration of helium-3 in lunar regolith is approximately 10 parts per billion. This seems insignificant, but considering regolith covers millions of square kilometers at depths of meters, the total quantity is substantial. Titanium-rich regions, like the Dark Maria, tend to have slightly higher concentrations, reaching 15 or 20 parts per billion. Why is helium-3 so valuable? It is ideal fuel for nuclear fusion. Unlike deuterium-tritium fusion, which produces high-energy neutrons and activates materials radioactively, Deuterium-helium-3 fusion produces mainly charged protons. These protons can be magnetically controlled, converting their energy directly to electricity with much higher efficiency. A single ton of helium-3 could generate energy equivalent to 50 million barrels of oil. The United States, with current energy consumption, would need approximately 25 tons of helium-3 per year to supply all its electrical needs. This is technically extractable from the moon with large-scale mining operations. The extraction process would involve heating lunar regolith to 600 to 700 degrees Celsius. At this temperature, trapped gases, including helium-3, are released. Processed regolith would be discarded and new material continuously fed. Calculations suggest it would be necessary to process approximately 150 million tons of regolith to extract 1 ton of helium-3. This may seem impractical, but terrestrial mining operations already move similar volumes. Copper and coal mines process billions of tons of material annually. In low lunar gravity, moving regolith requires less energy. Automated equipment could operate continuously with minimal human supervision. Several nations have expressed explicit interest in lunar helium-3. China mentioned helium-3 mining as a long-term objective of its lunar program. Russia, India, and Japan have also studied technical feasibility. Private companies have proposed exploration missions to map helium-3-rich deposits, but there are significant obstacles. First, fusion technology using helium-3 does not yet exist on a commercial scale. Experimental reactors have demonstrated controlled fusion, but none has produced more energy than it consumed. Second, infrastructure necessary for lunar mining would be an investment of hundreds of billions of dollars. Third, legal questions about ownership of extraterrestrial resources remain unresolved. The Outer Space Treaty of 1967 establishes that celestial bodies cannot be appropriated by nations, but it does not clearly address whether extracted resources can be private property. The United States approved law in 2015 allowing American citizens to own extracted space resources. Luxembourg approved similar legislation. But international consensus does not exist. Economic studies suggest lunar helium-3 would only become commercially viable if fusion reactors were developed, and if Earth-Moon transport costs dropped drastically. With current rocket technology, transporting mining equipment to the moon would cost tens of thousands of dollars per kilogram. Reusable launch systems could reduce this to hundreds of dollars. Helium-3 represents extraordinary potential, but realization depends on simultaneous advances in nuclear fusion, space transportation, and international law. While these pieces fall into place, the moon guards trillions of dollars in clean fuel beneath its dusty surface. And this same surface exhibits another intriguing phenomenon related to plasma and electric fields that transform dust into rigid structures. 34. The mystery of lunar bricks and plasma. Why does lunar dust sometimes behave like rigid solid? Apollo astronauts reported strange observations. Footprints remained incredibly well-defined, as if they had been impressed in cement. Regolith particles seemed to stick to each other more strongly than common terrestrial dust. Later research revealed that plasma and electric fields can temporarily weld lunar particles into cohesive structures. The phenomenon involves processes called plasma sintering. When solar wind strikes lunar regolith, it creates surface plasma, a cloud of electrons and ions. This plasma can penetrate between dust grains, creating microscopic bridges of molten material connecting adjacent particles. The effect is similar to welding on nanometric scale. Laboratory experiments attempted to replicate these conditions. Scientists placed simulated lunar regolith in vacuum chambers and bombarded it with ion beams imitating solar wind. In some cases, particles actually partially fused at contact surfaces. Ion energy heats contact points briefly above melting temperature, creating micro-welds when they cool. This sintering may explain why lunar footprints are so well defined. When astronauts stepped on regolith, pressure compressed particles together. Pre-existing plasma micro-welds, or those formed by mechanical stress, kept particles in compressed configuration. The result was a footprint that retained precise shape indefinitely. Another related phenomenon is the formation of agglutinates. These are regolith particles fused together by micro-meteorite impacts. When a micro-meteorite strikes, extreme heat locally melts regolith. Particles in the melting zone weld into larger fragments called agglutinates. These constitute approximately 30 to 60% of mature regolith. Agglutinates contain nanophase metallic iron incorporated in glass. Iron comes from minerals in regolith that were partially reduced during impact. These iron nanoparticles give mature regolith its characteristic dark color. The more agglutinates a soil contains, the darker it appears. Ancient regions with prolonged exposure to meteorite bombardment are darker. Electric fields can also create temporary dust structures. At the lunar terminator, where day meets night, extreme charge differences generate fields of thousands of volts per meter. These fields can align dust particles into chains or clusters through electrostatic forces. Researchers propose this ability to sinter lunar dust could be exploited for manufacturing. Instead of transporting construction materials from Earth, colonists could use microwaves or lasers to fuse regolith directly into bricks. Experiments demonstrated that lunar regolith heated to 1,100 degrees Celsius sinters into rigid material comparable to ceramic. Prototypes of lunar 3D printers would use this principle. A focused laser or microwave beam would melt regolith layers in specific patterns. Layer by layer, complex structures could be built. Without need for imported binders or cements, molten regolith would solidify into structurally solid blocks. Tests on Earth using lunar regolith simulants produced bricks with compressive strength of 30 to 50 megapascals. This is comparable to common concrete used in terrestrial construction. For lunar applications, where gravity is lower and structural loads reduced, these strengths are more than adequate. The European Space Agency developed a concept called lunar 3D printing, where autonomous robots would build habitats using only local regolith and focused sunlight. Large mirrors or lenses would concentrate sunlight to melt regolith. The process would be slow but completely self-sufficient, requiring no imported materials. Challenges include precisely controlling sintering temperature. Overheating vaporizes material and creates bubbles. Underheating results in weak bonds. Cooling rate also affects material properties. Rapid cooling creates glass, while slow cooling allows crystallization that can be stronger or weaker depending on composition. These lunar bricks formed by plasma, impacts, and artificial sintering represent transformation of loose dust into usable construction material. The lunar surface provides not just ground to step on, but abundant raw material for future structures. And below these vast plains of sintered regolith exist openings revealing entire networks of empty spaces. 35. Lunar pits, leading to underground networks. How many entrances to the lunar underworld exist? Since the discovery of the first lunar pit in 2009, more than 200 have been identified. But these pits are not just isolated holes. Growing evidence suggests many connect to extensive networks of lava tubes and caves, branching for dozens or hundreds of kilometers beneath the surface. The Moon may have interconnected cave systems rivaling Earth's largest underground complexes. The concept of underground networks comes from how lava tubes form. When lava flows beneath solidified surface, it rarely flows in a single channel. Lava seeks multiple paths, creating branch systems. On Earth, lava tubes in Hawaii and Iceland frequently have lateral tunnels, connected chambers, and multiple levels. On the Moon, with weak gravity and extremely low viscosity lava, these systems could be far more extensive. Modeling suggests individual eruptions could create tube networks covering thousands of square kilometers. A single lava tube complex could potentially connect multiple Maria regions. Indirect evidence comes from gravitational measurements. Grail data revealed subsurface linear voids in regions where no visible pit exists. These negative gravitational anomalies correspond to empty tunnels beneath the surface. Some of these anomalies extend for more than 100 kilometers in relatively straight lines. The Marius Hills region contains the largest known concentration of lunar pits. At least 17 have been identified in an area of approximately 300 square kilometers. Topographic analyses suggest many of these pits may connect to the same underlying tube system. If confirmed, Marius Hills could have a network of hundreds of kilometers of accessible tunnels. Ground-penetrating radar data from Japan's Selene mission detected echoes from empty structures up to 100 meters below the surface in multiple regions. These detections were not always directly under visible pits. This implies vast extents of lava tubes remain intact with non-collapsed roofs, invisible from the surface. Future explorers could enter through one pit and travel kilometers horizontally through tunnels. This would offer protected access to multiple regions without need to return to the hostile surface. Permanent bases could be established with interconnected chambers, each serving a different function: habitation, laboratories, greenhouses, storage. Exploration challenges include navigation in total darkness. Without sunlight penetrating, tunnels would be absolutely black. Lighting systems would need to be transported. Three-dimensional mapping using LiDAR would be essential to avoid collapsed tunnels or abysses. Direct communication with the surface would be impossible through solid rock, requiring communication relays. Some tunnel sections may be partially filled with regolith that fell through fractures in the roof over billions of years. Other sections may have floors covered with accumulated dust. Structural stability would be a concern. Although many tunnels have survived billions of years, lunar quakes or vibrations from human activity could destabilize fragile sections. The possibility of water ice in deep tunnels is intriguing. If some tunnels connect to polar regions or pass beneath permanently shadowed craters, ice could have migrated into the interior through fractures. Deep tunnels in permanent shadow could contain accessible ice deposits without surface mining. Bioprospecting of lunar caves is a scientific consideration. Although life on the moon is extremely unlikely, deep caves are more protected environments than the surface. If terrestrial microorganisms were accidentally transported by past missions, caves would be the most probable locations for survival. Planetary protection protocols will require analysis before human occupation. Lava tube networks would transform lunar exploration from a surface enterprise to an underground civilization. Future lunar cities could exist entirely below ground, connected by kilometers of natural tunnels. The moon's internal structure may be much more accessible and habitable than its hostile surface. And this unexpected accessibility is partially related to another surprising property. The moon is less dense than it should be. 36. The moon's surprisingly low density. Why is the moon so light for its size? The moon's average density is only 3.34 grams per cubic centimeter. Earth has a density of 5.52 grams per cubic centimeter. This means the moon is approximately 60% as dense as Earth. For a rocky body the size of the moon, this low density is anomalous and reveals fundamental aspects about how our satellite formed. The difference cannot be explained only by surface composition. Lunar rocks brought by Apollo missions have densities of 2.9 to 3.3 grams per cubic centimeter, depending on type. Maria basalts are denser, highland and orthosites are lighter, but the average density of the entire moon is only slightly higher than these surface rocks. This implies the moon has a very small metallic core. On Earth, the iron and nickel core represents 32% of total mass and has a density of approximately 10 to 13 grams per cubic centimeter. This dense core significantly increases the planet's average density. The moon has a core, but it is proportionally tiny. Seismic data from Apollo missions and modern gravitational measurements confirm the lunar core has a radius of only 350 kilometers. This represents less than 2% of the moon's total mass. For comparison, Earth's core contains 32% of Earth's mass. The moon is predominantly rocky mantle and crust, with an insignificant metallic core. This iron deficiency strongly supports the giant impact theory. When Theia collided with primitive Earth, the metallic cores of both bodies merged and sank to Earth's center. The ejected material that formed the moon came mainly from the mantles of both bodies, which are made of lighter silicate rocks. Therefore, the moon inherited low density corresponding to mantle material. If the moon had formed independently from the same cloud of material that formed Earth, we would expect a similar proportion of iron. If it had been captured, it could have completely different composition. The moon's specific density, very low but not extreme, corresponds precisely to what we would expect from solidified terrestrial mantle material. Low density has practical consequences for exploration. Lunar surface gravity is only 16.5% of Earth's. This facilitates launches. Escape velocity is only 2.38 kilometers per second compared to Earth's 11.2 kilometers per second. Rockets launching from the lunar surface need less fuel, making it viable to return samples or eventually export resources. For mining, low density means heavy metal concentrations are rare. There are no iron deposits equivalent to those found on Earth. Lunar mining will focus mainly on silicates, oxides, and volatiles. Metals will need to be laboriously extracted from minerals where they exist in relatively low concentrations. The moon's internal structure reflects its density. It consists of a 30 to 60 kilometer thick crust, an approximately 1,200 kilometer thick mantle, and a 350 kilometer radius core. The mantle represents approximately 90% of lunar mass. It is composed mainly of olivine and pyroxene, silicate minerals rich in magnesium and iron. Density differences within the moon create interesting contrasts. Highland and orthositic crust has a density of approximately 2.9 grams per cubic centimeter. Maria basalts have a density of 3.3 grams per cubic centimeter. This 14% difference is sufficient to create the Mascon gravitational anomalies discussed earlier. The lunar upper mantle may contain small amounts of metallic iron in addition to silicate minerals. Experiments suggest that when the lunar magma ocean solidified, small amounts of iron may have been trapped in the mantle instead of sinking completely to the core. This dispersed iron contributes slightly to density, but does not form concentrated deposits. The moon's low density also affects its response to tidal forces. Less dense bodies deform more easily under gravitational stress. Precise measurements of lunar shape reveal it is slightly elongated toward Earth, a permanent tidal bulge of approximately 10 meters. This deformation is greater than would be in a body of Earth density. Lunar composition and density make it a world fundamentally different from Earth. It is more like exposed terrestrial mantle than complete planet. This difference shaped all of lunar geological history, from rapid cooling of the magma ocean to early cessation of volcanism. And this light internal structure is constantly tested by impacts raining from space. 37. Constant micro-meteorite showers. How many times is the lunar surface struck by space projectiles? Every second, multiple particles collide with the moon. These micro-meteorite showers are constant and relentless. Estimates suggest that approximately 5 tons of material strike the lunar surface daily. During 1 year, this totals about 1,800 tons of space material deposited on our natural satellite. Most of these impacts involve tiny particles. Dust grains with masses from micrograms to milligrams constitute the vast majority. These particles travel at velocities of 11 to 72 kilometers per second. Even microscopic particles carry tremendous kinetic energy at these speeds. A 1 milligram particle at 20 kilometers per second has energy equivalent to a small bullet. When these particles strike, they create microscopic craters. A 100 micrometer diameter grain traveling at 20 kilometers per second excavates a crater approximately 1 millimeter in diameter. Exposed surfaces on the moon are literally bombarded by millions of these microscopic impacts per square meter annually. The cumulative effect over millions of years is transformative. Solid rocks are gradually pulverized into progressively smaller particles. This process is a main component of regolith formation. What began as solid basaltic or anorthositic rock is slowly ground into fine dust through countless microscopic impacts. Equipment left on the lunar surface suffers degradation. Retroreflector mirrors installed by Apollo missions for laser ranging experiments showed decreased efficiency over decades. Analysis suggests microcraters on mirror surfaces, created by micro-meteorite impacts, diffuse reflected light. Each microscopic impact slightly degrades optical precision. Spacesuits are particularly vulnerable. During lunar walks, astronauts are exposed to constant bombardment. Although the probability of being struck by a large particle is low, microparticles constantly strike. Suit materials are designed to resist, but prolonged exposure would cause degradation. Long-term surface missions will need additional shielding. Bombardment rate varies with the moon's orbital position. When the moon moves through cometary debris streams, as during meteor showers observed from Earth, impact rate increases dramatically. The LADEE mission detected increases up to 10 times in dust density during meteor showers like the Geminids and Perseids. These events create temporary dust clouds. When impact rate increases, more material is launched from the surface. Some of this debris reaches velocities sufficient to enter temporary orbits around the moon. The lunar exosphere thickens slightly during these events, although it remains far more tenuous than any planetary atmosphere. Larger impacts, though rare, are more spectacular. Tennis ball-sized meteorites strike the moon approximately once per week. These impacts create flashes visible from Earth with appropriate telescopes. NASA operates a monitoring program that has recorded more than 400 impact flashes since 2005. The largest observed flash occurred in March 2013. A meteorite estimated at 40 kilograms struck the moon at approximately 90,000 kilometers per hour. The impact created a crater approximately 20 meters in diameter and a flash as bright as a magnitude 4 star. This event released energy equivalent to 5 tons of TNT. For future lunar bases, protection against micro-meteorites will be critical. Surface habitats will need multi-layer shielding. Outer layer would absorb impacts, vaporizing projectiles before they penetrate. Inner layers would contain fragments. Spacing between layers allows vapor cloud to expand and dissipate energy before striking pressurized structures. Loose regolith is effective shielding. A layer of only 2 meters of regolith stops practically all micrometeorites. Larger projectiles are so rare that risk is acceptable. Habitats covered with regolith would be well protected. This is an additional reason to consider underground habitats in natural lava tubes. Lunar vehicles operating on the surface also need protection. Uncrewed rovers can use simple shielding, but crewed vehicles require robust protection to ensure safety during surface journeys of hours or days. Designs include double aluminum layers with intermediate spacing. Constant micrometeorite showers are reminders that the lunar surface is a dynamic and hostile environment. Every second, space projectiles strike, excavate, vaporize, and reshape the upper layer. What appears as static landscape is being constantly bombarded and transformed on microscopic scales. And these impacts are just one of many forces that have made the moon the fascinating and challenging world it is today. 38. The Earth-Moon binary system. Is the moon really a satellite or something more? Astronomers have debated for decades whether we should classify the Earth-Moon system as planet with satellite or as a binary system. The proportion between the masses of the two bodies is extraordinary. The moon has 1.2% of Earth's mass. For comparison, Mars's moons, Phobos and Deimos, have only 0.0000002% of Martian mass. The moon is proportionally the largest natural satellite of any rocky planet in the solar system. This unusual proportion led some scientists to propose that Earth and the moon form a binary planetary system. In astronomy, a binary system occurs when two bodies of comparable mass orbit a common center of mass called the barycenter. In the Earth-Moon system, the barycenter is located approximately 4,671 kilometers from Earth's center. This places the barycenter within Earth's volume, but not at the center. For truly binary systems, the barycenter is in space between the two bodies. Pluto and its moon Charon form an authentic binary system. Charon has 12% of Pluto's mass, and the barycenter is in empty space between them. Both bodies visibly orbit this point in space. Earth and the moon do not meet this technical criterion, but come closer than any other planet-satellite system among rocky planets. Earth's motion in response to the moon is measurable and significant. Earth's center describes a circular orbit of approximately 4,671 kilometers radius once per lunar month, while both orbit the Sun. This motion causes detectable variations in Earth's apparent position seen from distant spacecraft. The Voyager missions, when photographing Earth from billions of kilometers away, would have detected the oscillation caused by the moon if they had sufficient precision. Observatories on Mars could easily detect this oscillation with modern telescopes. The mutual gravitational influence is profound. The moon does not merely orbit Earth, the two bodies dance together around the Sun in complex choreography. The moon's trajectory through space never forms loops around Earth like typical satellites. Instead, the moon follows a slightly wavy orbit around the Sun, always convex, always curving toward the Sun. This is unusual. Most moons have orbits that clearly circle their primary planet when viewed from the Sun. The moon technically orbits the Sun in an orbit perturbed by Earth's presence. Some argue this reinforces the binary system perspective. Two bodies orbiting the Sun together, gravitationally coupled. The total mass of the Earth-Moon system is dominated by Earth, which contains 98.8% of combined mass. But in terms of angular momentum, the moon carries a much larger proportion. Approximately 80% of the Earth-Moon system's angular momentum is in the moon's orbital motion. only 20% is in Earth's rotation. This angular momentum distribution is crucial evidence for the giant impact theory. The impact transferred an enormous amount of angular momentum to the ejected material that formed the moon. This angular momentum was preserved in the lunar orbit and continues governing system dynamics today. The Earth-Moon relationship continues evolving. Each year, the moon recedes approximately 3.8 centimeters due to tides. In billions of years, when the moon is significantly more distant, its influence on stabilizing Earth's axis will diminish. But the system will remain gravitationally coupled, dancing around the sun as an inseparable pair. The Earth-Moon system represents a unique example in the solar system. It is not technically binary by strict definition, but is extraordinarily close. This special relationship between our two worlds shaped the history of both in ways scientists are still discovering. And a fundamental part of this relationship is the specific gravitational force the moon exerts, determined by its mass and size. 39. Why lunar gravity is only 16% of Earth's. What determines the strength of gravity on a celestial body? The simple answer is mass and radius. The moon has a mass of 7.34 x 10^22 kilograms. Earth has a mass of 5.97 x 10^24 kilograms. Earth is approximately 81 times more massive than the moon, but surface gravity does not depend only on mass. It also depends on the body's radius. Surface gravity is calculated by the formula G, or GMR2, where G is the gravitational constant, M is mass, and R is radius. The moon has a radius of 1,137 kilometers. Earth has a radius of 6,371 kilometers. Earth is 3.67 times larger in radius. When you combine smaller mass and smaller radius in the formula, you get lunar surface gravity of 1.62 meters per second squared. Earth's gravity is 9.8 meters per second squared. Dividing, lunar gravity is approximately 16.5% of Earth's, or about 1/6. This means an object weighing 60 kilograms on Earth would weigh only 10 kilograms on the moon. An astronaut could carry 6 times more mass with the same effort. This reduced gravity had profound and visible effects during Apollo missions. Astronauts hopped instead of walking because it was more efficient. Each step could cover several meters. When they fell, they did so in slow motion. A dropped object took longer to hit the ground. A thrown rock traveled much farther before falling. Low gravity also explains why the moon cannot retain atmosphere. For a gas molecule to gravitationally escape, it needs to reach escape velocity. For the moon, this velocity is 2.38 kilometers per second. For Earth, it is 11.2 kilometers per second. Gas molecules at room temperature have average velocities of hundreds of meters per second. For light gases like hydrogen and helium, a significant fraction of molecules have velocities above lunar escape velocity. These molecules simply fly into space. Over millions of years, even heavier gases like oxygen and nitrogen are gradually lost. Lunar gravity is simply too weak to retain atmosphere permanently. Low gravity facilitates space launches from the lunar surface. A rocket launching from the moon needs to reach only 2.38 kilometers per second to escape completely. From Earth, it needs 11.2 kilometers per second. This represents an enormous difference in fuel requirements. Launching from the moon requires approximately 1/6 the energy needed on Earth. This advantage makes the moon potentially valuable as a launch base for deeper solar system exploration. Materials mined from the moon could be launched to orbit at much lower energy costs than launching from Earth. Space stations could be built with lunar materials transported economically. For colonists, low gravity presents medical challenges. Astronauts in zero or low gravity experience bone loss, muscle atrophy, and cardiovascular changes. Lunar gravity of 16% may be sufficient to prevent some of these effects, but it is unclear if it is sufficient for long-term health. Studies in lunar habitats will be necessary. Exercise in lunar gravity would be fundamentally different. Lifting weights would be 6 times easier. But resistance exercises would still work because mass does not change. Pushing or pulling massive objects still requires force, even if they weigh less. Weighted suits could simulate Earth loads for exercise. Lunar gravity also affects how liquids behave. Spilled water would fall more slowly and splash differently. Fountains would spray higher, bubbles in liquids would rise more slowly. These effects would need to be considered in life support system design that handles water and other fluids. Structural construction would be simpler in some aspects. Buildings could be taller without collapsing under their own weight. Beams could span greater distances. But engineers would still need to consider accelerations during lunar quakes or meteorite impacts. Structures would need adequate strength even though static loads are smaller. Lunar gravity of 16% shaped everything about how the moon evolved and how humans will explore it. It is strong enough to keep structures on the ground, but weak enough to facilitate movement and launch. It is this intermediate gravity that makes the moon one of the most accessible destinations for permanent human colonization. And this same gravity was insufficient to maintain the internal heat necessary for active geological processes. 40. Dead plate tectonics and frozen crust. Why does the moon not have earthquakes caused by plate tectonics? The answer is simple but profound. The moon never had plate tectonics. Its crust solidified more than 4 billion years ago and has remained essentially frozen since. There is no plate movement, no subduction, no seafloor spreading, and no crustal recycling. The surface we see today is, in fundamental aspects, the same that existed billions of years ago. Plate tectonics requires specific conditions. The mantle needs to be hot enough for vigorous convection. The crust needs to be relatively thin and brittle. There must be liquids, especially water, to lubricate subduction zones. Gravity needs to be strong enough for dense plates to sink into the mantle. The moon does not satisfy these conditions. The lunar interior cooled rapidly after formation. Small bodies have a greater surface-to-volume ratio, so they lose heat more efficiently. The lunar core is tiny, representing less than 2% of total mass. This means there was little residual thermal energy from formation and little radioactive decay to generate continuous internal heat. Seismic analyses from Apollo missions revealed the moon has a structure of rigid layers. The crust is 30 to 60 kilometers thick. The mantle is solid to depths of at least 1,000 kilometers. Only in the inner core and possibly at the mantle's base are there partially molten regions. The lunar lithosphere, the rigid outer layer, encompasses practically the entire mantle. On Earth, the lithosphere is only 100 kilometers thick. Below it, the asthenosphere is partially molten and allows tectonic plates to slide. On the moon, there is no asthenosphere. Crust and upper mantle form a continuous rigid layer hundreds of kilometers thick. This rigidity prevents any plate tectonic type movement. The lunar surface shows evidence of thermal contraction but not expansion or lateral movement. As the interior cooled over billions of years, total volume decreased slightly. This created thrust faults, rocky scarps where crust was pushed over itself. These scarps, called Lobat scarps, are dozens of kilometers long and up to 100 meters high. The Lunar Reconnaissance Orbiter mission identified more than 3,000 of these thrust faults. Some are geologically young, with ages of only 50 million years. This indicates the moon is still shrinking, though very slowly. The lunar radius has decreased approximately 100 meters in the last 4 billion years. This contraction rate is minuscule compared to terrestrial tectonic processes. There is no modern active volcanism on the moon. The most recent eruptions occurred approximately 1 to 2 billion years ago. Since then, the mantle has cooled too much to generate magma. Without volcanism or tectonics, there is no recycling of surface materials. The crust we see today will remain unchanged for billions of years, except for new meteorite impacts. This geological stability has advantages for colonization. There is no risk of destructive earthquakes caused by plate movements. There are no active volcanoes to threaten settlements. The surface is predictable and stable. Structures built today will remain geologically safe indefinitely. But there are also disadvantages. On Earth, plate tectonics concentrates mineral resources. Subduction zones create rich metal deposits. Volcanism brings valuable minerals from the mantle. Crustal recycling distributes useful elements. On the moon, resources are distributed more uniformly and generally in smaller concentrations. The absence of tectonics also means the moon has no dynamo-generated magnetic field. Planetary magnetic fields require a convecting liquid core. The small lunar core solidified billions of years ago. Without a magnetic field, the lunar surface is directly exposed to solar wind and cosmic radiation, creating additional challenges for human exploration. The moon's frozen crust preserves a complete record of impacts dating back more than 4 billion years. On Earth, tectonics erased ancient craters through subduction and volcanism. On the moon, craters are permanent. This makes the moon an invaluable archive of bombardment history in the inner solar system. And this ancient, immobile surface has accumulated peculiar properties in its soil that surprised the first explorers. 41. The lunar soil that sticks to everything. Why is lunar dust so clingy? Apollo astronauts quickly discovered that lunar regolith had an irritating property. It stuck to absolutely everything. Boots, gloves, tools, scientific instruments, helmet visors, and interior surfaces of the lunar module became covered with a thin layer of dust that was almost impossible to remove. Harrison Schmitt described it as an unresolved operational challenge of lunar exploration. The explanation lies in the physics of electrically charged particles. On Earth, dust is continuously discharged by moisture in the air and by collisions with other particles. On the moon, there is no atmosphere. Regolith particles are electrically charged by solar ultraviolet radiation and solar wind bombardment. Electrons are ejected from grain surfaces, leaving them with positive charge during the day. At night, when solar wind dominates, electrons are absorbed and particles acquire negative charge. These electrical charges make particles attract to conductive surfaces like metal or spacesuit fabric. Electrostatic forces can be surprisingly strong on microscopic scale. Particle shape aggravates the problem. As discussed earlier, lunar regolith grains have sharp and irregular edges. These angular shapes increase surface area and create more contact points. When charged particles touch a surface, microprojections interlock mechanically, reinforcing electrostatic adhesion. During Apollo missions, astronauts tried multiple techniques to remove dust. Brushing was minimally effective. Vigorous shaking removed some dust, but not all. Using special lunar duct tape worked temporarily but soon saturated with dust. No method was completely satisfactory. Dust entering the lunar module was particularly problematic. In pressurized environment, particles floated in microgravity before settling. They covered all surfaces, infiltrated electronic equipment, and were inhaled by astronauts. Schmitt developed symptoms of lunar hay fever after significant exposure. Dust also caused mechanical problems. Spacesuit joints experienced accelerated wear. Rubber seals were cut by abrasive particles. Scientific instruments overheated when dust covered thermal radiation surfaces. Cameras had degraded image quality from dust on lenses. Post-mission studies examined why dust was so problematic. Analyses revealed individual grains had a nanometer glass coating created by Micro-Meteorite impacts. This vitreous coating is an electrical insulator, allowing charges to remain on particles for long periods without dissipating. For future missions, dust mitigation is an engineering priority. Proposals include active electric fields that would repel charged particles. Electrostatic coatings on suits and equipment could create repulsive barriers. Compressed air cleaning systems could blow dust off before astronauts enter habitats. Some designs propose external porches, where astronauts would remove outer layers of spacesuits contaminated with dust. Suits would be stored externally, accessed through rear hatches. Astronauts would enter habitats through docking rings, never bringing dirty outer layers inside. Other concepts involve cleaning suits using ultrasonic vibrations. Specific frequencies could dislodge particles without damaging fabrics. Combined with electric fields to repel loose particles, this could be more effective than mechanical methods. The European Space Agency tested prototypes of surface coatings that minimized dust adhesion. Superhydrophobic materials, although designed to repel water, also repel dry particles through nanoscale texture. Coated surfaces accumulate up to 90% less dust in tests with lunar simulants. Sticky lunar dust represents a significant challenge that needs to be solved before long-duration missions. It is not just a nuisance, it is an operational risk for equipment and a potential health risk for crews. And this electrically charged dust not only sticks to surfaces, but can be lifted into clouds that create visible phenomena. 42. Electrostatic dust storms. Can the moon have dust storms? This seems impossible without atmosphere. Storms require wind, and wind requires air. But the moon has a related phenomenon, electrostatic dust levitation. Intense electric fields can suspend charged particles above the surface, creating something similar to dust clouds. These electrostatic storms may have been observed by Apollo mission astronauts. The mechanism involves the lunar terminator, the moving line between day and night. During the day, solar ultraviolet radiation ejects electrons from dust particles, giving them positive charge. At night, electrons from solar wind plasma are absorbed, giving negative charge. In the terminator region, there are adjacent zones with opposite charges separated by only kilometers. This charge separation creates electric fields of hundreds to thousands of volts per meter. These fields are sufficiently intense to exert significant force on charged dust particles. Particles smaller than 10 micrometers in diameter can be lifted against weak lunar gravity, rising meters or even dozens of meters. Observations from Surveyor 7 in 1968 captured visual evidence. Images showed rays of diffuse light extending above the lunar horizon after sunset. These rays were consistent with sunlight scattered by suspended particles. The geometry suggested dust was being lifted specifically in the terminator region. Gene Cernan and Harrison Schmitt, while in lunar orbit during Apollo 17, reported observing tenuous glow on the lunar horizon before sunrise. They described it as vertical bands of luminosity that appeared and disappeared. The most plausible interpretation is they were seeing sunlight scattered by electrostatically levitated dust clouds. Instruments from the LED mission in 2013-2014 detected dust at orbital altitudes, confirming particles are being launched from the surface. Although meteorite impacts contribute, variations in dust density correlated with terminator position suggest electrostatic levitation is also active. Computer simulations modeled the process in detail. When the sun rises at a given lunar location, the transition from nighttime negative charge to daytime positive charge takes minutes to hours. During this transition, transient electric fields can be particularly intense. These spikes can launch particles more violently than steady-state fields. Meteor showers intensify the phenomenon. When the Micro-Meteorite impact rate increases during events like the Geminids, more dust is mechanically ejected. This newly launched dust enters the electric field environment and can be additionally levitated. LADY detected significant increases in altitude dust during known meteor showers. For surface equipment, electrostatic dust storms represent a risk. Charged particles can accumulate on sensitive surfaces. Solar panels can be degraded. Optical sensors can be obscured. Electronic equipment can experience electrostatic discharges when charged. Dust clouds pass. Future missions will need active electric field monitoring. Sensors would detect when conditions favor intense dust levitation. Sensitive operations could be postponed during high-risk periods. Critical equipment could be shielded or retracted during predicted storms. Astronauts performing extravehicular activities also need to be aware. Walking through a region of intense electric field could accumulate significant charge on the spacesuit. Although not necessarily dangerous, sudden electrical discharges when touching grounded objects would be disconcerting and could damage sensitive electronics. Some scientists propose using electric fields intentionally. Electric grids around habitats could create exclusion zones where dust is actively repelled. This could keep areas clean without need for constant mechanical cleaning. Experiments on future missions will test if this approach is practical. The Moon's electrostatic dust storms are reminders that even apparently static environments have active dynamic processes. Invisible electric fields constantly move particles, creating phenomena that defy intuition. The Moon has no atmosphere, but still has something analogous to weather, electrical variations that move dust in predictable but surprising patterns. 43. The Moon as Solar System. History Archive. Why is the Moon called a geological time machine? While Earth constantly erases its own past through plate tectonics, erosion, and volcanism, the Moon preserves intact records of events that occurred more than 4 billion years ago. Each crater, each regolith layer, and each rock fragment tells part of the primitive solar system's story. The lunar surface is literally a physical archive of billions of years of cosmic history. Preservation on the Moon is extraordinary because 3 terrestrial destructive processes are absent. First, there is no atmosphere to cause erosion by wind or rain. Second, there is no liquid water to dissolve minerals or transport sediments. Third, there is no plate tectonics to subduct ancient crust and create new. What forms on the Moon remains essentially unchanged indefinitely. The oldest lunar craters date from 4.3 billion years ago. They preserve records of the late heavy bombardment, a period when the inner solar system was struck by a swarm of asteroids and comets. On Earth, any crater from that period was completely erased. Subduction recycled oceanic crust where most impacts occurred. Erosion wore down continental craters. Lunar regolith is a layered archive. Each centimeter of depth represents millions of years of accumulation. Micro-Meteorite impacts deposit material ejected from distant craters. Solar wind particles are implanted. Impact glasses formed in specific events are preserved. Scientists can literally read temporal history by analyzing regolith cores. Apollo samples revealed fragments with multiple ages mixed together. A handful of regolith can contain 3 billion-year-old impact glass, 3.5 billion-year-old basalt, and 4.4 billion-year-old anorthosite. Each fragment is a witness to a specific geological event. Together, they tell a complex story of volcanism, impacts, and surface processes. Noble gases trapped in regolith provide a record of solar activity over time. Helium, neon, and argon isotopes from solar wind have been implanted continuously for billions of years. Variations in isotopic ratios reflect changes in solar wind composition and intensity. The Moon recorded the complete history of solar evolution from youth to current middle age. Craters of different ages show how bombardment rate changed with time. Ancient surfaces like highlands have extremely high crater densities, reflecting intense bombardment more than 4 billion years ago. Younger surfaces like Maria have fewer craters, documenting much lower impact rate in the last 3 billion years. Scientists use crater counting to date planetary surfaces throughout the solar system. Calibration comes from the Moon, where we have absolute ages from Apollo samples. By counting craters and images and comparing with lunar calibrated curves, we can estimate surface ages on Mars, Mercury, and Jupiter's moons. The Moon also preserves records of terrestrial events. When large impacts strike Earth, rock fragments are launched into space. Some of these fragments eventually fall on the Moon. Terrestrial meteorites on the Moon could preserve samples of primitive Earth from periods no longer available in Earth's geological record. Finding these terrestrial meteorites is a scientific objective for future missions. They would be extremely rare but invaluable. They could contain minerals or even microbial fossils from Earth 4 billion years ago, before complex life evolved. The Moon may be guarding secrets about terrestrial life's origins. Regolith also records cosmic radiation history. High-energy atomic nuclei from deep space create specific isotopes when they strike lunar minerals. By measuring concentrations of these cosmogenic isotopes at different depths, scientists reconstruct cosmic radiation history and solar activity. Variations in the interplanetary magnetic field left signatures in regolith. During periods when the solar magnetic field was more intense, fewer galactic cosmic rays reached the inner solar system. These periods appear as layers with lower cosmogenic isotope production. The Moon recorded decades and centuries of solar magnetic variability. Future sample return missions will have specific objectives to recover deep regolith cores. Drilling to 10 meters would provide samples representing hundreds of millions of years. Detailed analyses would reveal solar climate history, bombardment rate variations, and changes in solar wind composition. The Moon is a unique library of planetary history. Each rock is a page, each regolith layer is a chapter. By carefully reading this archive, scientists reconstruct not just lunar history, but the history of the entire inner solar system. And this historical knowledge directly informs plans to transform the Moon from passive archive to active home for humanity. 44. Future lunar bases and human settlement. When will humans return to live on the Moon? After more than 50 years since the last Apollo mission, multiple space agencies plan to establish permanent presence in the next 2 decades. NASA's Artemis program aims for crewed landings in the mid-2020s. China announced plans for a lunar base in the 2030s. The European Space Agency and Russia are developing similar concepts. The era of lunar settlement is beginning. The most favorable locations are at the lunar poles. Permanently shadowed craters contain water ice, a critical resource for life and fuel production. Simultaneously, nearby peaks receive almost continuous sunlight, providing reliable solar power. Shackleton Peak, near the South Pole, is illuminated 80 to 90% of the time. This is ideal for solar panels. The Lunar Gateway Base, a space station in lunar orbit proposed by NASA and international partners, will serve as a way station. Astronauts would transit through Gateway before descending to the surface. Supplies would be stored in orbit. Scientific missions would be coordinated. Gateway would function as a lunar spaceport. Surface habitats will likely be modular and expandable. Initial designs will accommodate 4 astronauts for periods of weeks to months. Later modules will expand capacity to dozens of permanent residents. Some concepts propose inflatable structures covered with regolith for protection against radiation and micro-meteorites. Lava tubes are serious candidates for long-term habitats. Once identified and explored, these natural tunnels would provide vast protected spaces. Pressurized modules could be installed inside the tubes. Solid rock walls would completely block radiation. Stable temperatures would eliminate need for intensive thermal control. In situ resource production is essential for sustainability. Extracting oxygen from lunar regolith is technically feasible. Regolith is approximately 40% oxygen by weight, bound in minerals. Chemical or thermal processes can release this oxygen. It serves for breathing and as rocket oxidizer. Water ice from polar craters will provide water for drinking, hygiene, and agriculture. Electrolysis splits water into hydrogen and oxygen. Hydrogen can be fuel or combined with captured carbon dioxide to produce methane. Self-sufficient bases will minimize dependence on terrestrial resupply. Energy will come primarily from solar panels. At the poles, where illumination is almost continuous during half the year, panels will provide stable power. Batteries will store energy for nighttime periods. Eventually, small nuclear reactors may supplement solar power, providing reliable baseload. Lunar agriculture will use pressurized greenhouses, direct sunlight through transparent windows, or LED light powered by solar panels will grow plants. Hydroponics or aeroponics will conserve water. Plants will provide fresh food, recycle carbon dioxide, and improve residents' psychological well-being. Manufacturing using 3D printing will transform regolith into structural components. Tools, replacement parts, and even habitat expansion modules will be produced locally. This will drastically reduce transportation costs. Eventually, lunar bases will export manufactured materials to orbital stations. Helium-3 mining is a long-term objective. If nuclear fusion using helium-3 is developed, the Moon will become a supplier of fuel for a clean global energy system. Large-scale mining operations would employ hundreds of workers and generate significant revenue. Medical challenges persist. Effects of 16% lunar gravity on long-term human health are unknown. Studies at initial bases will determine if lunar gravity is sufficient to prevent bone loss and muscle atrophy. Regular exercise and possibly rotating habitats may be necessary. Psychological isolation will be a serious challenge. Residents will be 3 days' journey from Earth, but effectively isolated for months. Careful crew selection, psychological support, and regular communication with family will help. Well-designed habitat environments with private and common areas will be essential. Lunar governance and law are being developed. The Artemis Accords, signed by multiple nations, establish principles for peaceful exploration and resource use. Questions about land ownership, mining rights, and legal jurisdiction are still being negotiated internationally. Within 20 to 30 years, a permanent lunar base inhabited by dozens of people is a plausible scenario. Within 50 years, a community of hundreds living and working on the Moon is possible. The transition from exploration to colonization is beginning. And when the first permanent residents arrive, they will experience one of the most iconic sensations of the lunar experience: the simple act of moving through low gravity. 45. Why astronauts hop on the Moon? What is it really like to walk on the Moon? The iconic images from Apollo missions show astronauts hopping in slow motion across the lunar surface. This peculiar mode of locomotion was not just for fun, it was literally the most efficient way to move in lunar gravity of 16% of Earth's. Each step became a hop. Each movement was a ballet of physics in action. On Earth, walking involves complex coordination of muscles and gravity. You push against the ground with enough force to propel yourself forward and slightly upward. Earth's gravity pulls you back quickly, your foot hits the ground, and you repeat the process. Each step takes a fraction of a second. On the Moon, the same muscular force launches you much higher and farther. The weak gravity of 1.62 meters per second squared does not pull you back quickly. You spend more time in the air. A normal step becomes a hop that can cover 2 to 3 meters horizontally and elevate you half a meter vertically. Apollo astronauts discovered this quickly. Neil Armstrong and Buzz Aldrin on Apollo 11 initially tried to walk normally. They found it was inefficient and tiring. In later missions, astronauts developed the kangaroo hop, a technique where they pushed with both feet simultaneously and hopped forward. This technique took advantage of lunar gravity characteristics. With less apparent weight, leg muscles had excess energy. Instead of fighting it, astronauts channeled it into forward momentum. The result was a mode of locomotion that seemed effortless and even joyful. The maximum speed astronauts achieved was approximately 3 to 4 kilometers per hour using hops. This may seem slow, but with an 80-kilogram heavy spacesuit, it was quite efficient. In lunar gravity, this suit weighed only 13 kilograms. Still, inertia remained, making direction changes challenging. Stopping was particularly difficult. With so much mass in motion, stopping quickly required planning. Astronauts learned to reduce speed gradually instead of attempting sudden stops. Eugene Cernan described nearly not being able to stop before running to the edge of a crater. Falling was another unique experience. With weak gravity, falls happened in slow motion. Astronauts had time to react, adjust position, and cushion impact. Most falls resulted in relatively soft landings. The spacesuit with portable life support system acted as a protective backpack. John Young, during Apollo 16, jumped vertically in the air and saluted the American flag. He reached impressive height with minimal effort. The images perfectly captured the strangeness of lunar physics. Movement that would be impossible on Earth became trivial on the Moon. For future long-duration missions, lunar locomotion will be refined. Lighter and more flexible spacesuits will allow more natural movements. Pressurized vehicles will transport astronauts over long distances. But for external work near bases, hopping will continue being an efficient method. Some engineers have proposed exoskeletons or mobility assistance systems. Small thrusters could provide additional impulse. Energy recovery systems would capture energy from each step and use it in the next. But the simplicity of natural hops may be hard to beat. Training for lunar locomotion happens at various terrestrial facilities. Pools with suits adjusted for neutral buoyancy simulate some aspects. Aircraft in parabolic flight provide brief periods of simulated lunar gravity. But no simulation perfectly replicates the real experience of moving on the lunar surface. The experience of hopping on the Moon represents more than a transportation method. It is a physical manifestation of being in a different world with different physics. Each hop reminds astronauts they are no longer on Earth. It is freedom of movement impossible at home. It is a dance with gravity that inspired millions watching from Earth. These iconic hops across the lunar surface encapsulate something fundamental about human space exploration. We are adaptable creatures who quickly learn to function in alien environments. The Moon is not our natural home, but humans demonstrated they can not only survive there, but move with grace and efficiency. And when future generations establish permanent residence on the Moon, they will develop their own movement culture, perhaps creating sports and dances possible only in lunar gravity. Apollo astronauts' hops were just the beginning of a long history of humans learning to live and thrive in the only place beyond Earth we have ever walked.